Hello there and welcome to Physics with William, where difficult ideas are allowed to slow down a little, sit comfortably for a while, and make themselves understandable without shouting. Tonight we are settling in with one of those phrases that sounds confident, familiar, and just a little magical until you stop and ask what it actually means. Virtual particle. It has the sort of name that seems ready-made for science documentaries, late-night conversations, and diagrams with arrows shooting in all directions. It sounds like something half real, half ghostly, perhaps a tiny visitor that flickers into existence, does some mysterious business behind the scenes, and then vanishes before anyone can catch it in the act. And in a great many popular explanations, that is more or less how it is presented. Empty space, we are told, is never truly empty. It seethes, it bubbles, it buzzes with fleeting particles appearing and disappearing all the time. There is a certain charm to that picture. It makes the vacuum sound lively. It makes physics sound dramatic. It also happens to plant a great deal of confusion right at the start. So before we go too far, let me ask you something simple. Where are you listening from tonight? And what sort of hour is it there right now? Is it late? Properly late? The kind of late where the house is settled and the world outside has gone quiet enough that your own thoughts seem louder than usual? Or is it one of those in-between times when the day has not quite let go but the evening has started to loosen its grip? There is something fitting about that, really, because the subject we're dealing with tonight lives in a similar sort of in-between place. Not quite everyday intuition, not quite the spooky fantasy it is often made out to be, but somewhere in that more interesting territory where ordinary language starts to struggle and physics keeps going anyway. And if you find this sort of slow walk through strange ideas soothing, useful, or simply a pleasant way to ease yourself out of the day, I would be very grateful if you gave the video a like and perhaps subscribed as well. It helps this small and sleepy corner of science find other people who enjoy learning without being pelted by urgency. Now then, I should probably warn you that virtual particles are one of those topics that can become more confusing the harder one tries to make them sound exciting. So tonight we are going to do the opposite. We're going to be patient with them. We're going to let the phrase sit in front of us for a moment and look at it carefully, because with a name like virtual particle, trouble has already arrived in the room before the explanation has even begun. That is often the way with physics. The first difficulty is not the mathematics or the experiments or the strange conclusions. The first difficulty is the words. We carry ordinary words into extraordinary territory and then act surprised when they begin to wobble. A particle sounds like a tiny object, something with a location, something that might be too small to see, but is, in principle, still the sort of thing one could point to and say there it is. And virtual sounds as though it means almost real, or temporarily real, or real in some thin and provisional way. Like a digital fireplace, or a virtual meeting, or one of those mock-ups of furniture that looks convincing right up until you try to sit on it. Put the two together, and the phrase seems to promise a small thing that is not fully real, but not fully unreal either. A temporary bit of matter, perhaps, a brief blip of existence, a particle with commitment issues. You can see why that image catches on. It is intuitive, it is vivid, it gives the imagination something to hold. If you say that forces between particles can be described in terms of virtual particles, many people immediately picture little messengers being tossed back and forth like invisible tennis balls. If you say that the vacuum has something to do with virtual particles, they imagine a dark emptiness crowded with tiny entities popping in and out of being. It feels concrete. It feels satisfyingly mechanical. And sometimes it is even taught that way in a first pass, because human beings do seem to need a story before they can tolerate the truth that the actual picture is more subtle. But the trouble with a convenient story is that it begins to fossilize. What starts as a rough teaching aid becomes a supposed fact. The sketch becomes a portrait. The metaphor becomes a mechanism. And before long, people are arguing over whether a virtual particle can be detected, whether it lives for a short time, whether it borrows energy from nowhere, whether it is a real thing after all if it has measurable effects. One can spend a very long time wandering around those questions and never notice that the real problem was smuggled in with the label itself. The phrase suggests the wrong category. It invites the mind to treat a useful feature of a calculation as though it were a tiny object running around inside nature by itself. This is not because physicists are trying to trick anyone. It is more that the history of physics is full of cases where a name survives long after it has stopped being helpful. There are many such examples. An atom was once named from a word meaning indivisible, which turned out to be rather optimistic. Planet means wanderer, which was a good observational description but hardly the whole story. Even the word particle itself can mislead, especially in modern physics, where the entities involved do not behave like tiny billiard balls in any ordinary sense. Still, names stick. Language is conservative. Once a term gets into textbooks and lectures and popular science books, it digs in like an old piece of furniture that everyone has learned to walk around, even if no one would choose to bring it into the house today. Virtual particles are one of those pieces of furniture. To understand why, it helps to begin not with some exotic edge of physics, but with the very human urge to imagine that every successful explanation must correspond to little hidden objects performing literal actions. It is an understandable urge. If a lamp switches on when you press a button, we like to think in terms of something travelling through the wire, something doing the job. If one thing influences another, we often want a little courier in the middle. A force seems easier to picture if we imagine an exchange. A calculation seems more trustworthy if every part of it can be translated into a little miniature drama. This instinct is not foolish. In many areas of life it is extremely useful, but nature does not sign any contract promising that whatever helps our intuition will also be ontologically tidy. Quantum field theory, which is the framework in which virtual particles usually appear, is not especially concerned with protecting our instinct for miniature dramas. It is a theory that works with astonishing precision, yet the way it works does not always map neatly onto the kinds of pictures our minds prefer. In that framework, when physicists calculate the probability of certain processes, they often use diagrams as bookkeeping devices. Those diagrams can include internal lines, and those internal lines are commonly referred to as virtual particles. Already you can hear the problem forming. A line in a diagram receives a noun that sounds like an object in the world, and then the imagination races ahead as if the line were a hidden camera image of what nature was literally doing all along. It would be a little like drawing a route on a map and then deciding that the blue line itself must be physically painted across the countryside. The map was useful. The route was meaningful. You may very well get where you're going by following it, but the line was part of the representation, not a stripe lying in the grass. Something similar happens here. A virtual particle is part of the machinery of a description. It belongs to a way of organizing a calculation. It is not, in the usual sense, something that flies out into the world and can be caught in a detector as an actual particle can. Now, if that sounds disappointing, do not worry. Physics remains strange enough without needing extra decorations. In fact, I would argue it becomes more interesting when we stop forcing it into the wrong kind of story. There is a particular kind of disappointment that comes from learning that a famous explanation was oversold, but there is also a deeper satisfaction in seeing why the oversimplification was tempting, and why the truth is not less beautiful, only less cartoonish. Virtual particles are a very good example of this. They are not little half-existing marbles that dash in and out of reality, but they do tell us something important about how we calculate interactions in quantum fields, and about the gap between the mathematical tools we use and the mental images we casually attach to them. That gap matters more than it first appears. Much of the confusion around this topic comes from sliding back and forth between different meanings of real. In ordinary speech, real usually means existing in the physical world. In physics, the word can shift depending on context. A real particle, in the most relevant sense here, is one that satisfies the conditions required to exist as a detectable particle state. It can, at least in principle, travel to a detector and leave a measurable signal as an actual member of the particle spectrum. A virtual particle does not do that. It appears in the internal structure of a calculation, not as an independently observable object. So when someone says virtual particles are not real, they are not saying the theory is fake or the effects are imaginary. They are saying that the entities labelled virtual particles are not particles in the same observational sense as the outgoing particles of an experiment. This is where popular explanations often take a wrong turn, usually with the best intentions. They want to make quantum processes intuitive, so they reach for a picture that seems manageable. They say things like particles exchange virtual particles to exert forces on one another. That can be a tolerable shorthand if everyone remembers it as shorthand. Unfortunately, everyone rarely does. The phrase lands in memory as a literal mechanism. It becomes, in the mind, a hidden event taking place just beneath the surface of reality. Then someone hears that virtual particles can violate energy conservation for a very short time, and now the confusion has acquired a cape, a fog machine, and a line of souvenir merchandise. Soon enough, an accounting trick has become a ghost story. The part about borrowing energy is especially persistent, perhaps because it sounds mischievous and easy to remember. Physics, according to this version, allows the universe to take out tiny short-term loans as long as it repays them quickly enough. It is a charming image. It is also not a sound way to understand what is going on. The uncertainty principle is not a little note from nature authorizing temporary theft. Energy conservation is not suspended for a brief moment when no one is looking. That entire manner of speaking creates more problems than it solves. It invites people to picture exact values being flouted by actual entities, when the real issue is how certain quantities appear in intermediate steps of a formalism. Put plainly, it turns a subtle statement about theory into a slapstick scene involving the cosmic equivalent of borrowing your neighbour's ladder and pretending it never happened. Another reason the topic gets tangled is that some genuinely measurable phenomena are loosely linked, in public discussion, with virtual particles. The Casimir effect is one of the usual examples. So are certain corrections in particle physics calculations and certain ways of talking about radiation near black holes. People hear that such effects are real and conclude that virtual particles must therefore be little real things after all. But this is rather like saying that because a financial report accurately predicts a company's behaviour, every line item in the report must correspond to a separate physical object stored in a warehouse. The success of the method does not force a literal interpretation of every term used in it. A calculation can be physically meaningful without all of its intermediate ingredients being standalone furniture of the universe. This is not a minor philosophical quibble. It affects how one thinks about what physics is doing at all. There is a temptation to imagine that the best theory is the one whose symbols can all be directly translated into tiny mechanical stories. Yet modern physics often succeeds precisely because it is willing to use abstract structures whose individual elements do not all come with simple physical pictures attached. That can feel unsatisfying at first. We would often prefer a universe made only of things that can be turned into illustrations. But the universe has shown no particular loyalty to that preference. It appears, on the contrary, to be perfectly content with us having to work a bit harder. So tonight the task is not to strip away wonder, but to relocate it. The wonder is not that empty space secretly spits out countless tiny particles in the way cartoons suggest. The wonder is that human beings built a framework capable of predicting experimental results to extraordinary precision, even though the path from the formalism to our everyday intuition is far from straightforward. The wonder is that a phrase can become famous, misleading, and useful all at once. The wonder is that a line in a diagram can tempt us into telling a whole story about miniature hidden actors, when what we are really looking at is a disciplined way of keeping track of contributions to a process that the full theory describes more deeply. And perhaps that is why this subject is worth taking slowly. It is not only about virtual particles. It is about what happens whenever language reaches beyond the territory where it evolved. It is about the gap between image and structure, between storytelling and calculation, between the thing that helps us begin and the thing that remains when we stop needing training wheels. In everyday life, that gap is often small enough to ignore. In quantum theory, it is large enough to drive a very large truck through, although preferably not at this hour. Let us bring it a bit closer to the ground. Suppose you heard someone say that in empty space, particles are constantly popping in and out of existence. You might reasonably ask several questions. What kind of particles? Where exactly are they? Can we detect them? Do they have mass? Do they carry momentum? How long do they last? What does it mean to exist briefly? If they appear and disappear, what distinguishes that from ordinary particle creation and annihilation in an experiment? And once you start asking those questions carefully, the popular picture begins to fray. It is not that the underlying theory says nothing interesting about the vacuum, it says quite a lot. The vacuum in quantum field theory is not merely a blank void in the way classical common sense might suggest, but leaping from that to a bustling submicroscopic fireworks display of literal temporary particles is a conceptual shortcut with a lot of loose floorboards. That is why the title of our journey tonight matters so much. What a virtual particle really is, and why it is not real. The second half does not cancel the first, it sharpens it. A virtual particle really is something in the theory. It is not nonsense, not a mistake, not a purely decorative phrase. But what it is belongs to a more technical and more limited role than the name encourages us to imagine. It is real as part of a representation, as part of a calculational framework, as part of the machinery that lets physicists decompose and organize interactions in perturbation theory. It is not real as a directly existing particle state out there in the world, flying about between source and detector as a hidden microscopic object. And if all of that sounds like we are about to become very fussy about definitions, that is because we are. Definitions are where this subject either clears up or falls apart. The pleasant part is that the fussiness is not pedantic for its own sake. It actually rescues the topic from becoming mystical. Once one stops expecting virtual particles to be tiny secret objects, a great deal of the fog begins to lift. The question changes from what weird things are these little, almost particles doing in the vacuum to why does the formalism contain these internal contributions, and under what conditions does that language make sense? That is a less flashy question. It is also the better one. So as we ease into this, let us keep one guiding thought in mind. Whenever physics gives you a phrase that sounds too vivid, too cinematic, too eager to become a literal mental picture, it is often worth asking whether the phrase is serving understanding or merely decorating it. Virtual particle is one of the finest examples of a term that does both. It is useful, it is evocative, it is also a trap if left unexamined. And the first step out of that trap is to ask what kind of thing a particle must be in the first place, before we start attaching adjectives to it. Because before we can sort out what makes a particle virtual, or why the word real becomes so slippery here, we need to slow down and look at the older and more basic problem that has been waiting quietly underneath all along. What exactly do physicists mean when they say particle at all? That question sounds innocent enough at first. A particle. We say it as though the matter was settled, as though nature had kindly labelled everything in advance and left us only the easy task of reading the signs. In ordinary life, the word seems perfectly serviceable. A particle of dust, a particle of sand, a particle of smoke floating in a beam of afternoon light. Tiny things, yes, but still things. Small bits of matter with edges, positions, and the general courtesy to remain themselves from one moment to the next. If you had a powerful enough microscope, so the intuition goes, you could simply zoom in and see them more clearly. Small would become smaller, then smaller still, until eventually you reach the truly little building blocks, and there they would be, the final grains of reality sitting patiently at the bottom of the world. It is a very natural picture. It is also one that modern physics has spent a great deal of time politely dismantling. The trouble begins the moment we try to carry that everyday meaning into quantum theory without checking whether it still fits. Because in fundamental physics, A particle is not simply a tiny object in the way a breadcrumb is a tiny object. It is a term that survives from an older picture of nature, a picture that still works beautifully in some contexts, but begins to wobble once you ask deeper questions. And when a word survives beyond the conditions that made it comfortable, it often keeps the confidence while losing the clarity. Particle is one of those words. It sounds sturdy. It behaves more like a veteran actor still taking the stage long after the script has changed around it. Classical physics trained us to think in terms of objects moving through space with definite positions and velocities. Little bodies here, larger bodies there, all follow in trajectories that in principle can be known. Even when the objects are very small, the picture remains familiar. A grain of pollen jostled in water, a droplet in mist, a speck blown by the wind. The central idea is that the object is there, complete in itself, carrying its properties along as it goes. If you cannot find it exactly, that is your limitation, not the object's. It has a place whether or not you know it. It has a path whether or not you can track it. That classical instinct is deep in us. It is practical, reliable, and for everyday scales it earns its keep. Then along comes the quantum world and starts behaving in a way that makes the old confidence feel a bit overdressed. Consider something like an electron. In some situations it behaves exactly as though it were a particle in the familiar sense. It arrives at a detector in a localized way. It leaves a distinct signal. It transfers energy in chunks. If you build an apparatus to detect individual electrons, you do not receive half an electron here and the rest on Thursday. You get a click, then another click. There is a discreteness to the event that strongly invites the word particle, and not without reason. But that is only half the story. In other situations, the same electron behaves in ways that no little classical pellet should. It interferes with itself. It spreads. It is described not by a neat path, but by something more like a distribution of possibilities. Ask too insistently for its exact position and momentum at once, and the theory does not merely shrug and say your instruments are poor. It says the request itself is misframed. This is the point where the word particle begins to show its seams. Because what kind of particle is it that does not carry a tidy trajectory in the classical sense? What sort of little object passes through an experiment in a way that forces us to use wave-like descriptions, probability amplitudes, and states that do not resemble miniature marbles at all? It is not that the word is entirely wrong. It is that it has become partial, situational, and a bit overconfident about its jurisdiction. Photons behave similarly, perhaps even more mischievously. We talk about particles of light because light can be absorbed and emitted in discrete quanta. You can count detection events. You can speak meaningfully of 1 photon, 2 photons, and so on, and yet light also spreads, interferes, diffracts, and generally refuses to behave like a stream of tiny glowing bullets in any simple classical sense. If one clings too tightly to the particle image, the behavior becomes baffling. If one clings too tightly to the wave image, that becomes incomplete too. The uncomfortable but fruitful lesson is that both words point toward aspects of the behavior without exhausting what the thing is. That alone should make us cautious. If even the so-called real particles of quantum theory are already unlike the small hard objects our language suggests, then adding the word virtual on top of particle is likely to produce more confidence than understanding. Before we can say what a virtual particle is not, we need to see that particle itself is already a compromise between mathematical theory, experimental practice, and human intuition. One way to approach the problem is to ask how physicists actually use the term when they are being careful. In modern quantum field theory, what we informally call particles are better understood as excitations of fields. Now, that phrase can sound forbidding at first, but it is more helpful than it may seem. A field is something defined throughout space and time, not a little object sitting at a point like a bead on a string. The electromagnetic field, for example, is present everywhere. The electron field is present everywhere. Quark fields, neutrino fields, and the rest of the family likewise. A particle, in this framework, is not a self-standing bead made of tiny substance in the old mechanical sense. It is a quantized excitation of the relevant field, a state in which the field behaves in a way that produces the properties we identify with a particle. Already you can see the shift. The basic ontology, if one wishes to use a suitably grand word for what the theory says exists, is no longer a collection of little bits alone. It is fields, and the particle-like aspect emerges when those fields are excited in certain ways. This helps explain why the same entity can display both localized, countable behavior and extended wave-like behavior depending on the context. The language of particles remains useful because the excitations often do arrive in detector-sized chunks, but the underlying framework does not encourage us to picture them as tiny independent pebbles flying through an otherwise empty void. That last part matters especially because the particle picture becomes less and less universal the harder you look. In calm, everyday circumstances, speaking of particles is often fine. In a particle accelerator, it is still fine in a more technical and disciplined way. But in strongly curved space-time, in certain interacting systems, or in situations where the environment changes what counts as a stable excitation, the very notion of particle can become observer-dependent or approximate. That is a rather sobering sentence if you grew up imagining particles as the most basic and unquestionable ingredients of reality. Observer-dependent is not usually what one wants from the foundations of existence. One would prefer stones, not subtleties. Yet subtleties are what we get. There are circumstances in physics where one observer naturally describes a system as containing particles, while another observer, moving differently or situated differently, does not use the same particle count. There are situations in condensed matter where collective excitations behave particle-like enough to be given names and treated almost as particles, even though they are not fundamental objects at all, but emergent patterns in a medium. A photon is a classic example, a quantized vibration in a material. Nobody is tempted to think a photon is a tiny bit of independent matter floating through empty space. It is clearly a mode of the system, and yet it behaves in a way that invites particle language because the excitations come in discrete amounts and can be counted and manipulated. This should make us a little humbler about the word. Particle is often a useful label for a certain kind of excitation, a certain kind of stable or approximately stable mode that shows up in a detector as a discrete event. It is not always the name of a tiny self-contained thing that exists in the way common sense first imagines. Sometimes it is closer to a convenient way of speaking about how a field or system behaves under the conditions we care about. That does not make it unreal. It makes it contextual. And contextual things, while less comforting than pebbles, are very common in serious physics. The detector itself plays a surprisingly important role in this whole business. When we say a particle was observed, we usually mean that there was a localized, quantized interaction with some apparatus, a click in a detector, a track in a chamber, a flash in a crystal, an event. The particle concept is tied very closely to this kind of observational signature. It earns its status because the theory predicts and experiments confirm that the interaction occurs in countable chunks. But what travels between the source and the detector is not always well represented by the image of a tiny classical object tracing a fixed path. Much of the conceptual trouble comes from taking the detector event and projecting it backward into a full story about what the entity must have been doing at every earlier moment. Human beings are great lovers of complete stories. If there is a beginning and an end, we want a neat middle. If a detector clicks here after a source emitted something there, we naturally imagine a little traveller going from one to the other by a definite route. Sometimes that image works well enough, sometimes it quietly fails. Quantum theory has a habit of letting us keep the beginning and end while becoming evasive about the middle. Not because the middle is nothing, but because the classical story we would like to tell about it is too narrow. This is why one often hears that particles in quantum theory are neither exactly particles nor exactly waves. That phrase is true as far as it goes, though it can become a cliché if repeated too lazily. The deeper point is not that nature could not make up its mind as though electrons were dithering between career paths. The point is that particle and wave are both classical categories, and quantum objects are described by a formalism that reduces to one or the other only in certain limits or under certain conditions. We keep using the old words because they still capture pieces of the behaviour, but neither word fully governs the territory. There is something almost comical in this. We inherit a vocabulary from the age of mechanical intuition, then gradually discover that the world at small scales is built in a way that treats that vocabulary as a rough convenience, rather than a faithful portrait. Still, the words do not leave. They cannot. Language is slower than theory, and everyday teaching needs handholds. So the word particle remains. It continues to do honest work when treated carefully and dishonest work when taken too literally. Take the notion of identity, for instance. In classical life, one grain of sand is one grain of sand, another is another. Even if they look alike, we imagine they are distinct individuals with their own tiny biographies. But identical quantum particles are not individual in that old comfortable way. Swap two electrons and nothing physically observable changes. The theory does not treat them as little labelled beads with personal histories. They are excitations of the same field, and the bookkeeping of individuality becomes far stranger than classical intuition would prefer. Again, the word particle remains in use, but the image attached to it has become much less like a small object with a birth certificate. Or think about decay. A muon, for example, can be treated as a particle, and quite successfully so. Yet, it is not an eternal little object carrying its own fixed identity through all circumstances. It is a state that can transform, a mode with a certain lifetime and behaviour. The theory handles this elegantly, but the image of a tiny persistent nugget of matter begins to look less and less like the right mental furniture. The particle language is still useful, but it is not fundamental in the old pictorial sense. It is a disciplined shorthand embedded in a larger framework. All of this is worth lingering over because the phrase virtual particle takes every one of these complications and adds another layer. If the entities we call particles are already field excitations, context-dependent in some respects, and only approximately captured by the image of tiny objects, then calling something a virtual particle strongly risks suggesting a little ghost version of an already slippery idea. It sounds like a miniature thing with even less commitment to existence than usual. One starts to picture faint, translucent electrons wandering through the vacuum like shy phantoms. That is not physics. That is just the imagination doing unpaid overtime. A more careful habit of thought would begin here instead. When physicists say particle in a serious context, what conditions make that word appropriate? Usually the answer involves stable or approximately stable excitations that can appear as incoming or outgoing states in a process, and can be observed as discrete events. They have the right energy and momentum relations to count as actual detectable particles. They are not merely features of intermediate mathematical steps. They can, at least in principle, live long enough and cleanly enough to be part of the story told by the apparatus. That is already a more restrained definition than the everyday notion of a tiny object, but it is much safer. Once you have that in hand, a virtual particle no longer sounds like a real particle, with transparency settings turned down. It begins to look more like a placeholder inside a particular calculational expansion, something that resembles a particle in some mathematical respects, but does not meet the conditions required to be an observable particle state. It is not out there flying to a detector. It does not need to. It belongs to the internal scaffolding of the calculation. But to appreciate that properly, one first has to stop treating particle as though it automatically meant a tiny classical object in the first place. There is another subtle trap here, and it concerns the seduction of pictures. Feynman diagrams are wonderfully helpful, elegant little sketches that organise terms and calculations and help physicists keep track of interactions. They are also perhaps too good at looking like cartoons of actual microscopic events. A line comes in, another line goes out. Something is exchanged in the middle, and the mind instantly turns the page into a tiny movie. This is understandable. We are visual creatures. Give us lines and vertices, and we will invent a little theatre. But the diagrams are not photographs. They are not hidden camera footage of the subatomic world conducting business behind closed doors. They are visual aids for mathematical structure. It is precisely because the word particle is so pictorial that this misunderstanding thrives. Internal lines in those diagrams get called virtual particles, and the imagination immediately treats them as objects with temporary lives. But if one has already learned that even external particles are not just tiny balls, then one is better prepared to resist that slide. The internal line is not a little thing caught halfway through being real. It is a contribution to an amplitude, expressed in a language that borrows the particle concept without granting full particle status. That distinction can feel finicky until one notices how many confusions it clears away at once. It also helps dissolve the false mystery. Many explanations of modern physics accidentally manufacture wonder by being slightly misleading. They tell you that space is full of little particles flickering in and out of existence, and leave you to marvel at the strangeness. But I think the better kind of wonder comes from understanding why the theory tempts us to say that, why the phrase spread, why it half works and half fails, and why the underlying reality is subtler than the slogan. There is a quieter satisfaction in seeing exactly where intuition breaks and how physics repairs the damage without pretending the crack was never there. The funny thing is that our minds are not entirely wrong to crave particle language. Nature does offer particle-like behaviour. Detectors click, tracks appear, energies come in lumps, scattering experiments do produce incoming and outgoing states that are wonderfully described as particles. The trouble is not the word itself. The trouble is forgetting that it is part of a larger and less classical framework. Used carefully, it is a good servant. Used naively, it becomes a small tyrant bossing the imagination into mistakes. So when someone says the phrase virtual particle, as though its meaning were obvious, the safest response is gentle suspicion. Not hostility, not despair, just a quiet raising of the eyebrow. What exactly is being claimed here? Are we speaking about an observable excitation, or about an internal component of a calculation? Are we using particle language as a careful shorthand, or have we started smuggling in a tiny hidden object because the sentence sounds more cinematic that way? And if particle itself already requires this much care, then perhaps the next step is to look at the place where virtual particles most often acquire their mysterious reputation, not in detectors, not in hidden little movies of the vacuum, but in the diagrams and mathematical machinery, where those famous internal lines first start to look far more literal than they really are. That is where the vacuum enters, and unfortunately it enters wearing a reputation that is both deserved and slightly theatrical. By the time most people hear the word vacuum in physics, they have already picked up at least one dramatic idea about it. They have heard that empty space is not really empty. They have heard that it boils or buzzes or seethes or bubbles with hidden activity. They have heard that particles are constantly appearing and disappearing in it, like a sort of microscopic fireworks display that never gets tired and never needs a permit. And because those descriptions are vivid, they settle in the mind very quickly. One begins to picture outer space, or any patch of apparent nothingness, as a dark room full of tiny surprise guests leaping in and out of the furniture. The difficulty is not that this picture is completely disconnected from physics. The difficulty is that it takes something subtle and turns it into a literal cartoon. As often happens, the cartoon is easy to remember and hard to unlearn. When physicists say the vacuum is not empty, they do mean something important. They do not mean that the vacuum is secretly full of ordinary matter we somehow forgot to notice. They do not mean it is packed with tiny permanent objects waiting in the dark, and they do not mean that every patch of space is swarming with little particlets, in the everyday sense like fruit flies over a neglected bowl. What they mean is that in quantum field theory, The vacuum is not the same thing as classical emptiness. It is not simply a featureless blank in which nothing at all is going on. It is the lowest energy state of the fields, and those fields are the basic ingredients of the theory. Even when there are no real particles present, the fields themselves are still there. The vacuum is therefore not nothing in the sense of non-existence. It is a physical state, and like any physical state in quantum theory, it has structure. That last word is doing a great deal of work, so it is worth pausing over. Structure does not necessarily mean little objects darting about. It can mean patterns of correlation. It can mean non-trivial behavior in expectation values and fluctuations. It can mean that when you examine the theory carefully, the vacuum carries properties that matter for calculations and measurements. The problem is that structure is a restrained and technical idea, whereas tiny particles popping in and out is the sort of sentence people remember at parties. One sounds like a careful adult. The other sounds like gossip from the universe. To see why the vacuum refuses to stay quiet, we have to let go of the older intuition that empty space is simply a container. Classical thinking encourages that picture. Space is there, and things are in it. Remove the things, and what remains seems like a passive stage, a bare room with the furniture taken out. But in quantum field theory, the fields are not guessed inside space in quite that simple sense. They are part of the physical content of the world at every point. An electron field is there whether or not electrons are currently being detected as particles. The electromagnetic field is there whether or not there are photons on their way to a detector. So the vacuum is already different from an empty classical room before any dramatic language enters the conversation. It is not a blank container. It is the ground state of a collection of fields. Now ground state can sound comforting, as though we have found the quietest possible arrangement and are at last allowed to turn the lights down. But quantum theory is not especially fond of absolute stillness. In ordinary classical mechanics, a system can in principle rest exactly at minimum energy, silent and unmoving. In quantum theory, things are more subtle. The vacuum state is the lowest energy state, yes, but that does not mean every field value and every rate of change can be pinned down with the perfect stillness classical intuition would like. There are unavoidable fluctuations associated with the quantum nature of the fields, and here again language tempts us into mischief. Fluctuations sound like little objects appearing and vanishing. Often they are better understood as the fact that the vacuum state has non-trivial properties and does not assign perfectly sharp classical values to everything at once. This is where many explanations take the first wrong step. They hear that the vacuum has fluctuations and immediately translate that into a cinema of temporary particles being born and dying. It is a very brisk translation and a very misleading one. Fluctuations in a quantum field do not automatically mean there are real particles present in the way a detector would register them. The vacuum is not a room in which hidden pebbles keep materializing, knocking into the walls, and dissolving before the inspector arrives. That image borrows too much from classical object thinking, and not enough from the structure of the theory itself. A useful comparison might be this. Imagine a quiet sea on a calm day viewed from far away. It may look flat enough to call smooth, but if you come closer and pay proper attention, it is not truly still. There are patterns, ripples, relations between nearby points, movements too subtle for the casual glance. Now even that comparison must be handled with care, because the vacuum is not a substance like water, and its fluctuations are not little droplets jumping out of the surface. Still, the comparison helps us escape the childish image of nothingness as absolute blankness. A state can be empty of particles and still not be featureless. The vacuum also matters because what counts as a particle depends on the situation in a way that common sense does not immediately expect. In a simple setting, one can define particle states clearly enough and say that the vacuum contains none of them. But that neat statement belongs to a framework, not to an absolute universal picture that never depends on the observer or the background conditions. In curved space-time or under acceleration, the particle concept itself can become trickier. Different observers need not agree in the same way about what qualifies as a particle. That is not because reality is indecisive. It is because particle language is tied to how field excitations are defined relative to a given setup. So even before one says anything about virtual particles, the vacuum is already teaching a humbling lesson. Empty of particles is not the same as empty of physics. One of the reasons the popular picture persists is that the vacuum does have measurable consequences. This is very important. If the vacuum were only a philosophical curiosity, people would have less incentive to dramatize it. But the vacuum contributes to observable effects in the theory. Energy levels can shift. Forces can arise between objects under the right conditions. Field correlations in the vacuum are not empty formal decoration. They can matter. The temptation then is to say, well, if the effects are real, then there must be little real things in the vacuum causing them. But that move is not logically required. One can have real measurable consequences without the intermediate story involving tiny temporary particles being the best literal description. This happens all the time in science, though less dramatically. You can use a very successful model that includes terms, approximations, or internal constructions without insisting that every element of the model corresponds to a separate little object hiding in nature. Maps have contour lines. Balance sheets have categories. Weather models have pressure surfaces and idealized cells. Useful, often indispensable, but not all ontological furniture. The vacuum in quantum field theory is more structured than classical emptiness, and it can produce real effects, but the step from there to a crowd of invisible flash-in-the-pan particles is still a step too far. There is also a historical reason the boiling vacuum image proved so durable. It arrived during a period when physicists were learning how to calculate interactions using perturbative methods and graphical representations that were astonishingly effective. Those methods invite one to speak in terms of intermediate contributions that look particle-like in diagrams. Once that language met the already strange idea that the vacuum was not merely blank, the combination was irresistible. A public explanation that says empty space is alive with temporary particles sounds much more exciting than one that says the vacuum state of quantum fields has non-trivial fluctuations and correlations. The second sentence is better. The first one sells more books. Still, it would be unfair to pretend the dramatic version came from nowhere. There is an intuitive impulse behind it that is not entirely silly. If you're told that the vacuum influences measurements, contributes to observable quantities and differs from classical nothingness, it is only natural to ask what is in it. Human beings are not very comfortable with activity that has no little actors. We want movers when something moves. We want occupants if a room has effects. We want hidden machinery. So we translate field theoretic structure into the nearest familiar image, which is tiny objects doing things. Physics then spends the next several decades trying to recover from the favour. Part of the cleanup involves being very precise about the meaning of vacuum fluctuations. The phrase does not mean that one can point to a real particle in the vacuum and say there it is, at least not in the ordinary sense relevant here. Rather, it means that the vacuum state is not an eigenstate of every classically intuitive quantity you might like to assign sharp values to. Correlation functions in the vacuum are not trivial. If you probe the theory mathematically, the vacuum exhibits non-zero structure. This affects what happens when systems interact with the fields, and it affects calculations of physical processes. But that is already enough. There is no prize for turning every non-trivial feature into a swarm of invisible insects. Take the Casimir effect, which is often dragged into these discussions like a star witness who did not agree to the interview. Two conducting plates placed very close together in a vacuum experience an attractive force under the right conditions. This is a real effect. It has been measured. It is often described in popular accounts as the pressure of virtual particles outside the plates being greater than inside, or something similarly picturesque. That kind of explanation can be catchy, but it is not the only way to understand the effect, and many physicists would say it is not the most faithful way. One can account for the phenomenon in terms of how boundary conditions modify the vacuum state of the electromagnetic field and alter the energy of the system. that is already perfectly physical, perfectly meaningful, and much less committed to a literal picture of little particles ricocheting around like over-enthusiastic ping-pong balls. Something similar happens in discussions of black holes and Hawking radiation, where popular accounts often introduce pairs of particles appearing near the event horizon, one falling in and one escaping. Again, this is a story that can be useful as an entry point, but if it is treated as the final literal mechanism, it causes confusion. The more careful account involves quantum fields in curved space-time, observer-dependent particle concepts, and the way modes are defined relative to the background geometry. None of that fits neatly on a greeting card, so the pair creation story survives. But survivability is not the same as accuracy. The vacuum also refuses to stay quiet in a more conceptual sense, because it undermines the old fantasy that absence must be simple. Classical emptiness seems easy to picture precisely because it has nothing to say. The quantum vacuum, by contrast, keeps reminding us that the lowest energy state of a field theory is still part of the theory, still structured, still consequential. It is the calmest state available, but calmest does not mean mute. If anything, it is one of the most eloquent pieces of the framework because its properties show up in places where naive common sense would have expected a blank. There is a lesson in that which extends beyond this topic. Physics often advances not by discovering that the world contains more little objects than expected, but by discovering that the conditions, states, and relations we once treated as inert backgrounds have more content than we thought. Heat turned out not to be a fluid but statistical motion. Space and time turned out not to be rigid containers but dynamical in relativity. The vacuum turned out not to be simple absence but a physically meaningful state of fields. Again and again, the quiet backdrop steps forward and reveals that it had lines in the play after all. And yet, even with all this, we should resist the temptation to romanticize the vacuum into something mystical. It is not a magical reservoir of free particles waiting to leap into your laboratory whenever you need a dramatic explanation. It does not permit violations of energy conservation by a wink and a nod. It is not a loophole in reality. Much of the nonsense spoken in its name comes from taking informal phrases too literally, and then adding just enough quantum uncertainty to excuse any remaining gaps in logic. One ends up with a picture that is easy to say and hard to defend. A better way to think of it is this: the vacuum is the baseline state of the quantum fields, but baseline does not mean blank. Because fields are quantum objects, their lowest state retains non-trivial characteristics. Those characteristics can influence physical systems and enter observable predictions. When one calculates processes in perturbation theory, one often describes aspects of these interactions using language that sounds particle-like, and one may speak of virtual particles. But the vacuum itself is not best imagined as a crowded waiting room full of tiny visitors whose train is always arriving and departing at once. It is better imagined, if one must imagine at all, as a state whose quiet is more technical than absolute. This is also why the phrase empty space needs handling with gloves. Empty of what? Empty of matter in the everyday sense. Often yes. Empty of real particles depending on the state and the observer. Perhaps yes in a given context. Empty of fields. No. Empty of physical significance. Certainly not. Once the fields are fundamental, the vacuum inherits their presence even when no particle excitations are around. That alone should warn us against treating the vacuum as mere nothing dressed up in scientific language. It is not nothing. It is the lowest state of something. That distinction becomes especially important when people try to make grand claims about the universe coming from nothing and casually use vacuum language as though it were equivalent to philosophical non-being. It is not. The quantum vacuum is a richly defined physical state within a theory. It has laws, structure, and conditions. Calling it nothing is like calling a silent orchestra non-existent, because nobody is currently playing loudly enough for the back row. The instruments are still there, the arrangement is still there, and under the right conditions the consequences are measurable. Silence is not absence. Of course, this still leaves a practical question hanging in the air. If the vacuum has all this structure, how do physicists actually talk about it when they calculate things? How do these quiet but non-trivial features get encoded in the mathematics? How does one move from the statement that the vacuum is not classically empty to the enormously successful machinery used in real predictions? That is where the discussion starts to lean toward the formal side. It is where propagators, internal lines, perturbative expansions, and all the tidy visual shorthand of quantum field theory begin to enter. And once they do, the urge to mistake bookkeeping for tiny hidden objects becomes even stronger, because the marks on the page start looking suspiciously like miniature stories about what nature is doing between the starting point and the detector. That is where the page itself starts to cause trouble, because physics has a habit of drawing things that look far more literal than they really are. Once you step from broad ideas about fields and the vacuum into the actual work of calculation, you quickly meet a world of symbols, expansions, terms, and tidy little visual devices that help physicists keep track of what would otherwise become a hopeless tangle. And this is exactly the point where many intelligent and perfectly reasonable people begin to slide from useful representation into misleading picture. It is not because they are careless, it is because the representations are so good at looking like miniature stories. If you have ever seen a Feynman diagram in a book or lecture, you will know the sort of image I mean. A line comes in, another line goes out, there is a meeting point, perhaps an exchanged line in the middle, and the whole thing has the air of a comic strip about subatomic life. Something enters, something happens, something leaves. You can almost hear the tiny footsteps. The diagram seems to whisper that it is showing you the actual event in the world, reduced to a clean sketch. It looks like a map of what the particles really did, and yet that is not what it is. Not in the straightforward way the eye wants to believe. This is one of the central difficulties in understanding virtual particles. They appear first, or at least most memorably, as internal lines in those diagrams. The moment the line is drawn, the imagination promotes it from a mathematical contribution to a little object in motion. That promotion happens almost instantly. You do not even need to decide to do it. Your visual system does it for you. A line connecting 2 points looks like a path. A path suggests a traveller. A traveller invites a story. By the time you've reached the end of the diagram, you're no longer reading a piece of calculational shorthand. You are watching an invisible play. The problem is that the diagram was never intended to be a hidden camera recording of microscopic events. It is more like an efficient notation for terms in a perturbative expansion. That phrase sounds dry, but it matters. In many quantum field theory calculations, especially when interactions are weak enough for this approach to work well, physicists expand the full answer into a series of contributions. Each contribution can be associated with a diagram. The diagram helps organize what must be calculated. It tells you what kinds of mathematical pieces go together, how they are connected, and what sort of intermediate structures appear in that term. It is not a little movie. It is a compact way of keeping the bookkeeping under control. Bookkeeping does not sound glamorous, which is perhaps why people resist it. But bookkeeping is what saves the day. Without it, many of the most accurate predictions in all of physics would become unusable forests of algebra. The diagrams are brilliant partly because they spare the human brain from drowning in its own notation. They let you see, at a glance, the skeleton of a contribution to the calculation. What comes in, what goes out, how the interaction is represented, and how many powers of the coupling are involved. That is enormously useful. It is just not the same thing as a literal picture of tiny objects exchanging secret messages behind the scenes. One way to make peace with this is to think about other fields where diagrams organize reasoning without pretending to be direct portraits of reality. A circuit diagram is not a photograph of electricity thinking very hard. A subway map is not a bird's eye view in which all the bends and distances are preserved. A family tree is not a botanical specimen. Useful, precise within a task, and yet not identical with the world they help us navigate. A Feynman diagram belongs in that company. It is a structured representation with rules, Its power lies in what it lets you compute, not in how temptingly it resembles a cartoon of actual events. This is also why the little marks in the math matter so much. Each line and point corresponds to a mathematical factor. External lines are associated with the incoming and outgoing particle states, the things that can in principle be prepared or detected. Internal lines are associated with propagation between interaction points within the calculation. Vertices represent interaction terms from the theory. The full amplitude comes from combining these ingredients according to strict rules. None of this requires that the internal lines be interpreted as actual particles existing independently in the way the external states do. They are part of the machinery that builds the answer. That distinction between external and internal is not a fussy technicality. It is the whole game. External states are the ones linked to real particles in the sense relevant to experiments. They are on the physical mass shell, to borrow the usual phrase, which simply means they satisfy the conditions appropriate to observable particle states. They can be prepared far from the interaction and detected afterward. Internal lines do not have that status. They are integrated over. They do not correspond to freely propagating, directly observable particles. They are not constrained in the same way. They appear in intermediate steps of the computation, not as independent objects that could ring a detector bell on their own. This is where people often hear that virtual particles are off-shell and nod politely while not really feeling what that means. It means, in practical terms, that the quantities associated with those internal lines are not restricted to the values that an actual detectable particle would have to obey. They are not being treated as physically realized particle states traveling from one place to another. They are internal contributors to a mathematical expression. The line in the diagram marks their role in the calculation, not their secret career in nature as little temporary beings. There is a strong temptation at this stage to protest that if the line corresponds to propagation, surely something must be propagating. And yes, something is being represented. But what is being represented is not best understood as an actual particle, popping into being for a moment, doing a bit of work and then politely disappearing. It is better understood as part of the field theoretic contribution to the interaction amplitude. The propagator, which is the mathematical object associated with that internal line, does not simply announce the presence of a tiny object in transit. It encodes how disturbances or correlations are accounted for between space-time points within the formalism. Translating that directly into a little particle story is exactly the shortcut that creates confusion. This is one of those cases where ordinary language is almost too eager to help. The term propagator sounds like a thing that moves along and carries news, like a courier service for quantum gossip. The line looks like a route. The vertices look like meetings. Soon enough one is picturing a force as a literal toss and catch game. For some purposes that image can serve as a rough intuition, but once the question becomes what a virtual particle really is, the roughness starts to matter, because the same mathematics can often be reorganized or interpreted in different ways, and the internal lines are not sacred little beads embedded permanently in the furniture of the universe. They belong to a chosen perturbative description. That point is easy to miss because the diagrams work so well. If something helps predict scattering amplitudes to extraordinary precision, the mind wants to reward it with reality. Surely one thinks, what is this successful must be showing us what is really there. But science has many examples where successful intermediate structures are not best read as literal objects. Sometimes a calculational device earns its keep by organizing the problem elegantly, not by naming a separate thing in the world. The history of physics is full of tools that were useful beyond the literal truth of the pictures attached to them. One can respect the tool without turning every mark on the page into microscopic furniture. Another reason these little marks acquire too much realism is that perturbation theory itself encourages a piece-by-piece narrative. You start with a simple theory you can solve, then you add interactions as corrections. The answer grows as a series. Each additional contribution can be drawn. It feels almost like building the event step by step. But that stepwise feeling belongs to the approximation method. not necessarily to how nature unfolds itself in a literal temporal sequence. The calculation decomposes the problem into manageable pieces because that is how the mathematics becomes usable. Nature is under no obligation to break the process into the same little stages just because our notebooks do. In fact, one of the most important habits a physicist develops is learning when not to overread the scaffolding of a method. Scaffolding is indispensable while the building goes up. It tells you where to stand, what connects to what, and how to proceed without falling off the side. But once the structure is complete, you do not mistake the scaffolding for the building itself. Feynman diagrams are like that. They support calculation. They provide organization, intuition, and an extraordinary economy of thought. But mistaking them for literal microscopic narratives is rather like admiring the scaffolding so much that you forget what it was erected for. There is also the issue of gauge dependence and formulation dependence, though one need not become too technical to feel the force of it. In many theories, the way one performs the calculation and the intermediate quantities one writes down can depend on the chosen formalism. Yet the final observable predictions remain the same. This should already warn us against taking every intermediate element as a direct piece of reality. If different routes through the mathematics yield the same measurable outcome, then some caution is required before announcing that a particular internal line in one representation is a little invisible object truly running around inside nature. Observable results carry more ontological weight than the private furniture of a chosen calculation. This is not to say the mathematics is arbitrary. Far from it. The rules are strict. The formalism is disciplined. The contributions are not invented at whim. But strictness is not the same as literal pictorial truth. A sonata has strict structure without the notes being tiny objects in the air waiting to be found under the piano. A legal document can be rigorous without every clause corresponding to a separate physical event on the courthouse steps. The mathematics of quantum field theory is incredibly constrained, yet its internal devices should still be read with care. Let us make this more concrete. Suppose two electrons scatter off one another. In a simple perturbative treatment, one can draw a diagram in which they exchange an internal photon line. Popular descriptions will often say that the electromagnetic force here is mediated by a virtual photon tossed back and forth between the electrons. This is not completely useless as a first gloss. It captures the fact that the interaction is associated with the electromagnetic field, and that the internal line in the diagram is photon-like in the relevant mathematical sense. But if one then imagines an actual little photon being emitted by one electron and absorbed by the other as a real transient object, one has stepped too far. The internal photon is not a real observable photon state travelling between them. It is part of the amplitude calculation for the interaction. This becomes clearer if you notice that the full answer is not merely one neat diagram anyway. Depending on the level of accuracy required, one must include many contributions, corrections, loops, and alternative terms. The process is not exhausted by one clean little exchange picture. The diagram that looks most intuitive is often only the lowest order term in a much richer structure. If one tries to treat that one line as the literal event, one has ignored the very framework that gave the diagram meaning in the first place. The mathematics is telling you that the observable process receives contributions from many terms. The eye is telling you a fairy tale about one tiny messenger. The eye is entertaining. The mathematics pays the rent. Loops are another excellent place where little marks in the math start getting promoted beyond their station. In higher-order diagrams, internal lines can form closed loops. These contributions are crucial for corrections to masses, charges, and other measurable quantities. They help explain why the theory matches experiments so astonishingly well. But if one narrates every loop as a literal swarm of temporary particles spinning around inside the vacuum like frantic office workers, the picture quickly becomes absurd. What the loop represents is an internal contribution to the amplitude, not a hidden footage reel of subatomic commuters doing laps. This is especially important because such internal contributions can even diverge before renormalization is handled properly. The theory then instructs us in how to organise and absorb those infinities so that measurable quantities remain finite and predictive. Now imagine trying to treat every divergent internal feature as a straightforward little physical object. You would end up with a very strange zoo indeed. The sensible conclusion is not that physics has discovered a new species of invisible chaos, but that the internal structure of the calculation is not to be read naively as a direct catalogue of tiny things. And yet the language survives, because the alternative would often be unbearably cumbersome. Saying virtual particle is vastly quicker than saying internal line corresponding to an off-shell contribution in a perturbative expansion of the interaction amplitude. One cannot blame the shorter phrase for winning the race. The trouble begins only when the abbreviation starts pretending it was never an abbreviation. Physics is full of such shorthand. Most of the time it behaves itself. With virtual particles it developed theatrical ambitions. There is also a pedagogical reason the little marks become personified. Teachers are often trying to bridge a gap between intuition and formalism. A student who has never met quantum field theory can at least grasp the idea of an interaction being represented by an exchange something. So one starts there. One says think of it as a photon exchange, or a gluon exchange, or what have you. As a first foothold, that can be fair. The danger comes when the foothold becomes the house. Good teaching often begins with a simplification, but good learning requires noticing when the simplification has reached the end of its useful life. Perhaps the most honest way to put it is this. The marks in the math are not meaningless decorations, but neither are they miniature photographs of nature. They are disciplined symbolic devices that let us compute observable quantities. Their elements inherit names from particle language because that language connects naturally to external states and to certain aspects of the theory. Internal lines are called virtual particles because they resemble particle propagation in a technical, limited way. But they are not particle states in the ordinary observable sense. They are not things you can bottle, count with a detector, or watch slipping through the vacuum when nobody else is looking. This is why the phrase little marks in the math is not meant dismissively. The marks matter enormously. Without them, much of modern particle physics would become unreadable, but their importance lies in their role, not in their theatrical potential. They guide calculation, they encode contributions, they keep track of how the terms fit together. They are successful because the formalism is successful. The mistake is not in drawing them. The mistake is in forgetting what they were drawn for. Once you see that, a certain amount of fog begins to clear. Virtual particles are not ghost particles. They are not baby particles waiting to grow up. They are not particles that were real for a brief moment before returning to the world of abstract nouns. They are names attached to internal features of a calculational framework. Extremely useful features, yes. Deeply connected to the structure of the theory, certainly. But still not the same as the incoming and outgoing particle states that can be prepared and detected. The difference matters because without it, every explanatory picture starts to wobble. And of course, the wobble gets worse precisely because the diagrams are so temptingly visual. The better they are at helping us think, the more readily we start mistaking them for what is literally there. That is the next problem waiting quietly in the wings. Not the mathematics itself, but the peculiar power of a simple sketch to make us believe we're looking through a window instead of at a well-designed piece of notation. Part of the reason that confusion lasts so long is that Feynman diagrams are almost unfairly good at looking like pictures. Give a human being a set of lines, a few meeting points, and some arrows, and the mind starts narrating before it has been invited. One line comes in from the left, another leaves to the right, something gets exchanged in the middle, and within a second the whole page has turned into a tiny drama. We do not merely see a diagram, we see a sequence, we see an event. We see the microscopic world going about its business in a neat and orderly way that looks suspiciously as though it were drawn for our convenience. It is difficult not to feel that the image is showing what really happened. That feeling is understandable. It is also the beginning of the mistake. A Feynman diagram is not a photograph of an invisible process. It is not a slow-motion replay of what nature did between the beginning of an experiment and the end. It is not a secret surveillance image from inside the atom. It is a highly efficient piece of notation. It is a visual way of organizing mathematical terms in a calculation. The fact that it resembles a little story is useful up to a point, but the resemblance is not the same thing as literal truth. The diagram helps us compute the probability amplitude for a process. It does not necessarily tell us that nature itself unfolded in exactly the staged and orderly manner the sketch seems to suggest. This is one of the hardest habits to build in modern physics, partly because it goes against the way the human mind likes to work. We are very good at treating pictures as windows. If a chart shows a curve, we think of the quantity rising and falling. If a map shows a road, we think of the road itself. If a diagram shows a path, we assume something travelled along it. This is usually helpful. Most of the time the world rewards that instinct. But in theoretical physics there are many cases where the picture is a guide to the formal structure, rather than a literal portrait of hidden events. Feynman diagrams sit exactly in that awkward territory. They are visual enough to tempt us, and abstract enough to punish us if we take the temptation too seriously. There is a deeper reason they look so literal. The diagrams were designed to encode interaction terms in a way that reflects the structure of the theory. They are not arbitrary doodles. They preserve real information about what interacts with what, and how different contributions are connected. So the visual form is not meaningless. A line really does stand for a mathematical object associated with a field or a state. A meeting point really does stand for an interaction. The trouble is that once those pieces are drawn, the eye quietly adds something that the formalism itself does not require. It adds a tiny space and time narrative. It turns relation into event, connection into motion, and bookkeeping into biography. Take a simple example. Two electrons scatter off one another. A very common first diagram shows them exchanging an internal photon line. The beginner looks at this and immediately thinks one electron emitted a photon, the other absorbed it, and that is how the force happened. It seems perfectly reasonable. In some loose educational settings, it may even be presented that way because it gives the student somewhere to stand. But if that picture hardens into the belief that a real little photon literally flew from one electron to the other as a hidden object during the event, trouble begins. The internal photon in that diagram is not a real photon state, in the same sense as an actual photon that could be detected as an external particle. It is an internal contribution to the amplitude. The diagram is not telling you the exact little movie that occurred. It is telling you how one term in the perturbative expansion is organized. That distinction matters more than it first appears, because once you promote the diagram into a literal microscopic film, you start asking the wrong questions. Where exactly was the virtual photon at this moment? How long did it exist? Did it move faster than light? Did it borrow energy? Could it be stopped halfway? These questions feel natural only because the picture has already tricked you into treating the internal line as a thing moving through the world like an actor in a scene. In the formalism, however, the internal line is part of a mathematical object integrated over contributions. It is not a detectable traveller with a little passport and a very short life expectancy. There is also the matter of time in the diagram, which people often read much too casually. A Feynman diagram is usually drawn on a flat page with one direction informally treated as time, and the other as space or just visual separation. This immediately suggests chronology. First this happened, then that, then the outgoing particles emerged. But the diagram is not always best read as a literal time-ordered film strip. In many contexts, the drawing is simply a topological aid to the structure of the term being calculated. Rearranging the picture on the page does not necessarily change the underlying mathematics, as long as the connections remain the same. That alone should make one suspicious of overly literal readings. If bending a line or shifting a vertex on the page does not change the physics, perhaps the page was not a secret stage set after all. This becomes even clearer when one moves beyond the simplest tree-level diagrams into higher-order contributions. Then the pictures acquire loops, nested structures, and multiple internal lines that can be drawn in ways no honest person would mistake for a straightforward little process if they had not already been trained to do so. Yet because the first simple diagrams look so intuitive, people often continue narrating even the more complicated ones, as though nature were carrying out a little graphical performance. One ends up imagining clouds of temporary particles splitting, rejoining, circling, and vanishing like a troupe of very nervous acrobats. At that point, the picture is no longer helping intuition, it is replacing it with a visual superstition. The irony is that Feynman diagrams were never meant to function as naive, realistic pictures in the first place. Their genius lies elsewhere. Before them, many calculations in quantum electrodynamics were extremely cumbersome. The diagrams offered a way to encode complicated terms in their combinatorics in a form the human mind could actually work with. They made it possible to see the structure of perturbation theory without drowning in algebra. That was revolutionary. But a tool that improves human understanding by becoming visual always runs the risk of being mistaken for a direct image of reality. The better the tool, the stronger the temptation. A badly designed diagram would not create this confusion because nobody would want to romanticize it. A beautifully designed one is dangerous precisely because it feels so natural. It helps to remember that nature is under no obligation to arrange itself in ways that can be sketched on a page. A diagram is our device. It serves our method of approximation, our formal expansion, our choice of variables, our practical need to sort terms. The world does not hold committee meetings to ensure that electrons and photons behave in a way that makes tidy line drawings possible. If the drawings work, that is because the mathematics works. Their success does not automatically grant the sketches the status of microscopic documentary footage. A good comparison might be musical notation. A score is full of marks that correspond to real features of a performance. Pitch, timing, structure, relation, repetition. The notation is not arbitrary. A trained musician can read it and produce an actual piece of music. But nobody confuses the score with a photograph of sound. Nobody imagines that the black notes on the page were literally floating in the concert hall. The notation is powerful because it captures structure in a compact visual system. Feynman diagrams do something somewhat similar for interaction terms. They are not random, they are deeply constrained, but they remain notation. Their lines do not owe us literal microscopic careers. Another reason the diagrams are overread is that they flatter common sense at exactly the moment common sense is most likely to fail. The quantum world is hard to picture, and people naturally crave an image that restores a sense of grip. A Feynman diagram offers just that. At last, one thinks, here is something manageable. Here is a little sketch I can follow. Here is the force as an exchange, the process as a sequence, the event as a comprehensible mechanism. It feels like the theory has come down to earth, and for a first pass that relief is not worthless. But the cost of that relief can be high if it is never repaid. The student who stays at the level of literal diagrams often ends up more confused later, not less, because every deeper clarification sounds like it is taking something away. In truth, it is only correcting the false certainty the sketch created. This happens often in physics education. A teacher offers a simplified image because starting from complete technical accuracy would be unbearable. The image helps at first. Then the image outlives its usefulness, and the student must let it go or at least loosen their grip on it. Some manage this easily, others feel betrayed, as though the early intuition was a trick. It was not a trick, it was a temporary bridge. The mistake is not in building bridges. The mistake is in trying to live on them permanently. There is an even subtler issue here. Different formulations of a theory can organise the same physics in different ways. Different gauge choices, different calculational schemes, different reorganisations of perturbation theory can all lead to the same observable predictions. This should make us wary of assigning too much reality to the specific internal furniture of one visual representation. If the final measurable result is robust while the route through the mathematics can vary, then the intermediate picture is likely carrying a mixture of physical content and formal convenience. The observables deserve our deepest trust. The little internal actors in one diagram deserve a more modest status. This does not mean the diagrams are disposable or shallow. Quite the opposite. They carry deep information. They reflect symmetries, selection rules, conservation laws, and the structure of interactions in a compact and extraordinarily efficient form. A skilled physicist can look at a diagram and know immediately which contributions matter, which processes are allowed, which terms are suppressed, and where the difficult parts of the calculation will arise. That is not trivial. It is a profound triumph of representation. But triumph of representation is not the same thing as direct picturing of microscopic reality. One can admire the map without deciding the map is secretly the territory in flat disguise. The visual seduction becomes even stronger because the diagrams often line up with language people already know. One hears about exchange particles, mediator particles, interactions, scattering, emission, absorption. These are all meaningful words in context. They are not wrong. But as soon as the diagram is placed next to them, the mind stitches them into a polished little scene. An electron emits, a photon flies, another electron absorbs. The force is done. It sounds so clean. Too clean, really. The actual formalism involves amplitudes, superpositions, internal integrations, and a full quantum field theoretic structure whose relation to pictorial storytelling is partial at best. The clean scene is not wholly false, but it is not the whole truth either, and its clarity can conceal how much has been left out. There is also the common confusion between calculational order and physical occurrence. A perturbative expansion writes the answer as a sum of terms, often beginning with the simplest contribution and then adding corrections. This can make it feel as though nature first does the leading thing, and then politely adds the smaller details afterward. Of course, that is not what is happening. The expansion is our way of approximating the full answer. It is a strategy of calculation, not a timetable followed by the universe. Feynman diagrams inherit that structure. They feel sequential and constructive because the method is constructive. But method is not event. Approximation is not chronology. It is worth noticing how much the misunderstanding depends on our own habits of perception. If the same information were presented as a page of integrals and operator expressions, very few people would say they were looking at a hidden movie of nature. They would understand at once that the mathematics is a tool for calculation. But draw the equivalent structure as lines and vertices, and suddenly the page acquires narrative authority. This is a lesson not only about physics, but about human cognition. Vision is persuasive. A line can smuggle in a story more effectively than a paragraph can. We trust shapes long before we examine what they actually mean. Perhaps the clearest sign that Feynman diagrams are not literal pictures is that one physical process is generally described by many diagrams, not one. The measurable result comes from combining contributions. No single sketch is the event. The event is associated with the full amplitude, which in perturbation theory is built from a whole family of terms. So even if one were tempted to say, a given internal line represents what really happened, one would immediately face the problem that many such lines from many diagrams contribute together. Nature is not switching between a set of tiny cartoons and choosing one at random like a bored projectionist. The diagrams are pieces of a calculation, and the observable process is tied to their summed contribution. This is especially sobering when interference matters, as it often does. Contributions can reinforce or cancel one another in ways that make it impossible to maintain the fantasy that each diagram is a separate hidden event and the experiment simply picks one. The theory is not telling us about a bag of alternative little movies from which reality selects a winner. It is telling us how amplitudes combine. That is more abstract than ordinary intuition likes. but it is also much closer to the logic of the theory. Once this sinks in, virtual particles start losing their ghostly glamour. They cease to look like tiny temporary beings darting around in secret, and start looking like what they really are within this context, namely internal elements of a perturbative representation that borrow the language of particles without achieving the status of observable particle states. Their apparent life comes from the diagram. Their drama comes from our eyes. Their usefulness comes from the mathematics. These three things are not the same, and most confusion comes from blending them together. So when a Feynman diagram looks literal, that is not because it was built to deceive. It is because it is an elegant human artifact designed to make a complicated formal structure manageable. Elegance always carries a risk. It can make a representation feel more natural than it really is. It can tempt us to forget the difference between what helps us think and what the world is obliged to contain. The little sketch becomes a tiny myth. Then physics has to come back in with a broom and clear a path through the storytelling. And that path matters, because once we stop treating the diagrams as microscopic snapshots, we can finally ask the right question about the internal lines themselves. Not what tiny hidden object is this really showing, but what role does this thing actually play in the formalism? What kind of entity appears in the mathematics, resembles a particle just enough to inherit the name, and yet never arrives in a detector as a real one? That is where the phrase virtual particle begins to shed its costume and look much less like a creature and much more like a very peculiar career path for something that never actually shows up. There is something almost tragic about the career of a virtual particle, at least if one insists on thinking of it as a particle at all. It appears in the mathematics. It acquires a familiar name. It is drawn with a neat line in a diagram, sometimes even granted the dignity of direction and identity. It seems to take part in the action. It seems to mediate, connect, influence, perhaps even travel. And then, just when the imagination has promoted it into a respectable microscopic actor, physics quietly steps in and says, "Not so fast." This one never actually arrives. It does not appear in the detector as a real outgoing object. It does not survive as an independent particle state. It does not make it across the finish line into the category of things you can observe directly. It has a role, certainly, but it is a very peculiar role. It is central to the calculation and absent from the cast list of observable particles. That is what makes the phrase virtual particle so misleading and so memorable. It sounds like an ordinary particle with some slight reduction in status, as though it had done most of the necessary paperwork but failed one final inspection. One imagines something almost there, something momentarily existing in a provisional way, something halfway between a fact and a rumour. But the actual situation is less theatrical and more technical. A virtual particle is not a particle that nearly became real and then lost its nerve. It is a name for an internal contribution in a perturbative description, a piece of the calculation associated with internal lines in Feynman diagrams, a formal object that resembles a particle in certain mathematical respects without qualifying as an observable particle state. This is why the phrase that never arrives is so useful. Real particles, in the sense that matters here, are the ones that can appear as incoming or outgoing states in an experiment. They can be prepared. They can be detected. They live on the physical mass shell, to use the technical phrase again, meaning they obey the condition appropriate to actual propagating particle states. A virtual particle does not. It belongs to the interior of the calculation. It contributes to the amplitude, but it does not step out into the world as a finished item. It is not the guest who turns up at the door. It is more like an entry in the planning notes that helped organize the event. One of the simplest ways to feel the difference is to think about what a detector actually does. A detector does not care about the elegance of your diagram. It does not award points for internal lines. It registers localized interactions, energy deposits, tracks, flashes, discrete events. If a real photon arrives, or a real electron, or some other real particle state compatible with the apparatus, the detector may respond. That response is the sort of thing physicists can calibrate, count, and compare with prediction. But the internal virtual particle in a diagram is not something the detector is waiting to catch halfway through. It is not en route in that sense at all. It is part of the mathematical structure used to compute the probability of the overall process. This leads to a question that many people eventually ask, and quite reasonably so. If it is not observable, why call it a particle in the first place? The answer is that the internal line shares enough formal relation with particle propagation that the language becomes convenient, especially within perturbation theory. The internal line is associated with the same field one would associate with a real particle of that type. A virtual photon line belongs to the electromagnetic field. A virtual electron line belongs to the electron field. The resemblance is not invented from nowhere. But the resemblance is incomplete. The internal object is not constrained in the way a real particle is constrained. It does not satisfy the conditions required for an independently existing particle state that could be measured before and after the interaction as a proper member of the observable cast. The moment that distinction is forgotten, the strange career of the virtual particle gets rewritten as a tiny melodrama. It is born from nothing. It rushes between particles. It carries a force. It vanishes just in time to avoid the consequences, and everyone applauds the mystery. But this is not what the formalism is telling us. The formalism is telling us that when we calculate an interaction perturbatively, internal propagators appear as part of the terms in the amplitude. Calling them virtual particles is a shorthand. It is not a confession that the vacuum is crawling with brief little beings ducking in and out of legal existence. This becomes especially clear when one looks at the quantities associated with internal lines. Unlike real particles, they are not limited to the energy and momentum values that would make them actual free particle states. They are integrated over a range of internal values. They are, in that sense, off-shell. That phrase can sound intimidating, but it simply marks the fact that they are not on the same footing as detectable particles. They do not represent a particle moving through the world with the proper relation between its properties that an actual observed particle must have. They are internal degrees of the mathematical description. Necessary for the calculation, yes. Literally arriving as particles, no. There is something quietly important in that no. It does not mean the process is unreal. It does not mean the force is unreal or the interaction imaginary. It means that one should not confuse the intermediate formal device with an independently existing object. The scattering of two electrons is real enough. The measurable outcome is real enough. The contribution of the internal photon line to the amplitude is mathematically meaningful. But the virtual photon itself is not a real photon sneaking through the middle of the event like a courier with a forged badge. If this sounds like a subtle difference, that is because it is. But subtle differences often do the real work in physics. The trouble comes when people hear that virtual particles mediate forces and infer that forces are literally carried by little objects ricocheting between particles in a way the diagrams display. In some rough sense, this can be an acceptable teaching metaphor at first. It gestures toward the field-theoretic structure and toward the exchange character that appears in perturbative descriptions. But as soon as the student begins asking whether the exchanged object is real, measurable, or bound by the same conditions as a real particle, the metaphor begins to fray. If one is honest, it was fraying all along. Think again of that exchanged photon in electron scattering. The diagram invites the eye to say one electron emits a photon and the other absorbs it. That wording is not entirely crazy, but it becomes dangerous if it suggests a real free photon existed between the two. A real photon emitted by an electron would have to be a proper outgoing particle state, subject to the usual physical conditions. The internal photon in the scattering diagram does not have that status. It is not the same sort of object as the photon you could in principle detect after an emission process. It is an internal propagator, and that difference is exactly why the process can be described the way it is. There is a useful analogy here, though like all analogies it must be handled gently. Suppose you are balancing the finances of a complicated project. In your internal calculations, you may introduce intermediate quantities, accounting categories, or provisional entries that help organize the final budget. These entries are not fake. They matter. If you remove them, your bookkeeping collapses. But they are not all separate physical piles of money sitting in boxes somewhere in the office. They are internal devices that help produce the right final answer. A virtual particle is not an accounting entry in the everyday financial sense, of course. But the analogy captures something important. An internal role in a rigorous calculation is not the same thing as a directly existing physical object. The trouble with the borrowed energy story shows up here again. Because virtual particles do not satisfy the conditions of real particles, people often hear that they can somehow momentarily violate ordinary constraints and get away with it because of the uncertainty principle. This is one of those explanations that sounds rebellious enough to spread quickly and wrong enough to cause years of damage. The uncertainty principle does not grant the universe a license for temporary misconduct. It does not say that energy conservation can simply be ignored for a short time. What it means in the relevant context is subtler, tied to the structure of states and measurements, not to little particles taking out short-term loans from the laws of physics. The virtual particle is not a rogue particle exploiting a loophole. It is an internal contribution whose mathematical role should not be turned into a moral fable about rule-breaking. There is another reason the career of the virtual particle feels strange. It appears to mediate something without itself being an observable final product. We are used to causes that leave visible intermediates. If one person passes a letter to another, the letter can in principle be intercepted. If one billiard ball strikes another, the motion is visible. But quantum field theory often forces us to work with amplitudes and internal contributions that are not themselves separately observable in that way. The effect is visible in the total process. The internal structure used to compute it is not necessarily something nature offers up one piece at a time for inspection. This can feel unsatisfying because it denies us a certain kind of microscopic voyeurism. We would like to peek behind the experimental outcome and see the little hidden mechanism doing exactly what the diagram suggested. But physics is under no obligation to satisfy that desire. Sometimes the best theory gives us a way to predict outcomes with immense accuracy, without providing a simple classical-style story about hidden intermediate objects one could line up and interview. In fact, the more successful the theory becomes, the more temptation there is to grant literal status to its internal machinery. If a theory predicts results with extraordinary precision, then surely, one thinks, the things it mentions must all be real in the strongest possible sense. But that is too quick. A theory can be extraordinarily accurate while still containing intermediate devices whose ontological status is more modest. What matters first is what the theory says about observables and how its formal structure supports those predictions. Internal elements may be indispensable without being separately detectable objects. The history of science does not promise us a one-to-one correspondence between every useful calculational component and every piece of reality taken as a tiny self-standing thing. A more mature intuition begins to form once one stops asking where the virtual particle is and starts asking what task it performs. It links parts of the perturbative expansion. It encodes the contribution of an internal propagator. It helps represent how fields contribute to interaction amplitudes. Its job is not to arrive at the detector. Its job is to help make the prediction. This is why its career is so strange only if one insists on measuring it against the standards of real particles. Measured by the standards of the formalism, it is doing exactly what it is supposed to do. There is something almost bureaucratic about this, though perhaps at this hour bureaucracy is not the ideal image to summon. Still, it may help. Imagine a necessary internal memo in a large institution. Without it, the final decision could not be reached properly. It carries information through the process. It has a role in the internal structure. Yet it is not itself the final public decision, nor is it something the outside world receives directly. If one mistakes the memo for the final action, confusion follows. The virtual particle is like that, necessary inside the structure, not the thing that arrives as the public outcome. This also helps explain why the language of mediation can be both useful and dangerous. To say that the electromagnetic interaction is mediated by photons is true within the field theoretic framework, but the statement operates on several levels at once. When speaking of real radiation, real photons may indeed appear as actual particle states, but when speaking of the static or scattering interaction in a perturbative diagram, the internal photon line is virtual, not real. The mediation is formal and field theoretic, not a literal courier service staffed by temporary particles of light hurrying to and fro. If one forgets that, one starts imagining all forces as tiny exchange games, and the field concept quietly recedes into the background where it does not belong. The field is really the steadier character here. Particles come and go, at least as detectable excitations. Fields are the underlying entities in the theory. A virtual particle, then, is better thought of not as an independent thing with a brief and troubled existence, but as a way the perturbative language packages part of the field interaction into a particle-like form. It borrows the clothing of a particle, because that is useful in the formalism, but it never becomes a citizen in the full observational sense. It is not a failed particle. It is a different sort of theoretical animal altogether. This is why asking how long a virtual particle exists is often the wrong sort of question. The question assumes the virtual particle had the kind of existence a real particle has, only abbreviated. But the internal line is not a small traveller with a stopwatch over its head. It is not sitting inside the process as a temporary guest waiting to expire. The time language comes from over-literalising the diagram and from mixing it with the borrowed energy folklore. Once one remembers that the virtual particle is part of the internal amplitude structure, the question loses much of its grip. The career was never temporal in the everyday sense to begin with. It was formal. The same goes for location. Where is the virtual particle? Again, the question flatters the particle picture. It suggests that somewhere in the interaction region there is a tiny object with coordinates, however briefly. But the internal propagator is not best understood as a little localized bead occupying a spot and then vacating it. It is part of a mathematical expression relating interaction points in the formalism. Translating that into a tiny object with a short residence permit is an imaginative leap the theory itself does not force on us. One might wonder whether all of this makes virtual particles sound disappointingly unreal. In a sense, yes, if one was hoping for ghostly subatomic creatures. But it also makes them more interesting. Their significance lies not in being tiny secret objects, but in showing how far one must sometimes travel from ordinary intuition to do serious physics honestly. They are reminders that successful theories often carry layers of language, shorthand, approximation, and internal structure that do not collapse neatly into little mechanistic stories. They are signs of sophistication, not of magic, and perhaps that is the deeper lesson. The career of the virtual particle is strange only because we keep trying to hire it for the wrong job. We want it to be an actual microscopic traveller, a hidden object bridging the gap between cause and effect. The theory employs it differently. It uses it as part of the internal machinery of perturbative calculation. Once we stop demanding that it arrive like a real particle, we can appreciate what it really does. It helps us encode interactions in a field-based theory where the old object picture is already under strain. It lets us talk in a particle-flavoured way about contributions that are not particle states. It is useful precisely because it sits in that in-between formal role. And that in-between role points us toward the next difficulty. If virtual particles are not little real things flying back and forth, then what are we really saying when we describe forces using them? Are we just telling ourselves a simplified story because fields are harder to picture? Are exchange particles only a convenient language layered over something more basic? In other words, once the strange career of the particle that never arrives has been sorted out, we're left facing the broader question that has been quietly waiting behind it all along. namely what sort of story we're actually telling ourselves when we speak of forces, fields, and the hidden machinery of interaction. That broader question is really the heart of the matter, because virtual particles only become confusing when they are asked to carry more explanatory weight than they were ever meant to bear. Much of that weight comes from the way we talk about forces. We say one particle pushes another, or attracts it, or exchanges something with it, and all of those phrases seem to point toward a hidden mechanism we ought to be able to picture. But the history of physics is full of cases where the words we use to keep ourselves oriented also quietly smuggle in old intuitions that no longer fit the theory very well. Force is one of those words, field is another, and between them sits a story we tell ourselves because it is helpful, because it is elegant, and because, if we are not careful, it can start sounding much more literal than it really is. For most of human history, a force was easiest to understand when it looked like a push, or a pull in the ordinary sense. You push a door, you pull a rope. A cart rolls because something shoved it, or because gravity drew it downhill. The picture is mechanical, direct, and perfectly good for daily life. Even when classical physics became more refined, the old intuition survived. A force was still something that changed motion, and although the mathematical description grew more precise, the mental image remained reassuringly simple. One thing acted on another. The world seemed full of little episodes of her influence. Then electricity and magnetism complicated the picture. Charges could influence each other across space. Magnets could tug and twist without any visible contact. The old instinct was to ask what exactly was reaching across the gap. Surely something must connect the objects. Surely there had to be some hidden cord or pressure or transmission. Physics responded by developing the field concept, and this was one of the great conceptual shifts in all of science. Instead of imagining a force as a direct mysterious reach from one object to another, one could think of the source as creating a field throughout space, and the other object as responding locally to that field where it was. That was a major improvement. It replaced spooky action at a distance with a more structured picture. The field became the intermediary, not as a tiny messenger running back and forth, but as a physical entity spread through space. This was already a subtle idea, and it still is. We are much too used to it now to notice how strange it once sounded. A field is not a little object. It is not a mechanical linkage in the ordinary sense. It assigns values or properties throughout space and time. The electromagnetic field, for instance, is present everywhere, with different strengths and directions at different points. A charged particle responds to the field where it is. In that sense, the field concept already moved physics away from the old dream that all influence must be explained by tiny little pushes between hard objects. It asked us to think in a more distributed way. Even so, the field picture did not entirely satisfy the human appetite for a concrete hidden mechanism. We still like things that move and trade and carry. So when quantum field theory arrived and brought with it the language of quanta and excitations, it offered something very seductive. Now one could sometimes talk about interactions in terms of exchange quanta. A force could be pictured as involving the exchange of a photon or a gluon, or some other mediator in the relevant theory. This had real usefulness. It connected the field concept to particle language in a way that helped with calculations and, in some contexts, intuition. But it also reopened the door to an older mechanical hunger. Once the exchange picture took hold, people began quietly translating fields back into stories about tiny objects shuttling influence around. That is the story we tell ourselves. And it is not entirely false. That is what makes it sticky. In many perturbative contexts, speaking of interaction through exchange diagrams is perfectly sensible. It captures something about the structure of the theory and about the way certain contributions to amplitudes are organised. But it is still a story told in a particular language, from within a particular calculational strategy. The moment it hardens into the claim that forces literally consist of tiny temporary particles being fired back and forth like microscopic tennis balls, the story starts to outrun the theory. A good way to feel this is to compare the classical field picture with the exchange picture, and notice that each one highlights something different. In the classical field view, a charge generates an electromagnetic field, and another charge responds to the field at its location. No little courier is required. The influence is encoded in the field itself. In the perturbative quantum picture, one may describe certain interactions by diagrams involving internal photon lines. Those internal lines are then called virtual photons, and one says the electromagnetic interaction is mediated by them. The second language is not wrong, but it is narrower and more formal than it first sounds. It belongs to the quantum field theoretic calculation. It is not simply a more detailed literal movie hiding underneath the classical field picture. If anything, both descriptions are ways of organizing aspects of a deeper framework in different regimes. This is where people often make an innocent but important mistake. They imagine that the field is just a kind of average picture for large scales, while the real microscopic truth is the exchange of particles. But quantum field theory does not really support that neat hierarchy. It is not that fields are vague and particles are the crisp reality underneath. Quite the opposite in many ways. The fields are the more fundamental entities in the formalism, and what we call particles are excitations of those fields. Real particles are certain states of the fields. Virtual particles are internal features of perturbative calculations involving those same fields. So if one must choose which concept is structurally deeper in the theory, field is usually the steadier footing. That can feel backward, because particles seem more tangible. We imagine being able to count them, catch them, detect them, give them names and properties. Fields sound misty by comparison, too spread out, too abstract, too likely to drift into the sort of language that makes the average dinner guest look for the breadbasket. But tangibility is not the same as fundamentality. The detector clicks are real enough, yes, and particle language is often exactly the right way to describe those events. Still, the underlying formalism is written in terms of fields, not a little box of self-sufficient beads rattling around in the void. The particles emerge as excitations. The fields are there throughout. This matters because it changes what it means to say a force is mediated by something. In a simplistic particle exchange story, mediation sounds like a delivery service. One object throws a messenger. The messenger travels. Another object catches it. The force has been transmitted. It is satisfyingly mechanical, very tidy, and not quite the right level of truth. In the field picture, mediation is not a tiny object passing a note. It is the structure of the field and the interaction terms in the theory determining how systems influence one another. The exchange language can encode that in perturbation theory, but it does not replace the field concept with a miniature postal system. This becomes especially clear if one asks what happens in situations where the exchange picture is awkward, incomplete, or not the most natural language available. There are many such situations in physics. Strongly interacting systems, non-perturbative regimes, collective excitations, and effective theories all remind us that the neat exchange story is not the whole kingdom. Sometimes it is a good approximation. Sometimes it is an elegant calculational picture. Sometimes it is simply not the most illuminating way to think. The field concept, though itself subtle, is often more robust across these contexts. There is also a conceptual comfort in telling stories that make nature sound more like a machine built from tiny contact events. We are descendants of creatures who learned the world through touch, pressure, collision, and impact. It is no surprise that we trust those images. A field spread through space already asks a lot of us. A quantum field with excitations, amplitudes, and internal propagators asks even more. So when a simplified exchange picture offers us a return to something more graspable, we seize it with both hands, tiny things tossing influence around. At last, a story with verbs our ancestors would have approved of. But physics has a repeated habit of taking our favourite verbs and making them slightly embarrassing. Light is not just a wave in a medium. Gravity is not just a force in the Newtonian sense, heat is not a fluid, the vacuum is not a blank, and forces in quantum field theory are not merely little games of catch between hidden particles. Each time the older language survives because it still works somewhere, or at least still gestures in the right direction. Yet each time the deeper theory asks for more restraint than the inherited verbs would suggest. There is a very ordinary lesson hiding in all this. Explanations are not always mirrors, sometimes they are handles. A good handle lets you lift something heavy, even if the handle is not itself shaped like the thing you are lifting. The exchange particle story is often such a handle. It can help a newcomer grasp that interactions are structured, quantized, and tied to specific fields. It can help them understand why different forces are associated with different mediator types. It can help them stop thinking in terms of crude action at a distance. All of that is useful. The trouble comes only when the handle is mistaken for the object itself. One sees this most clearly in the way people talk about static forces, such as the ordinary electromagnetic attraction or repulsion between charges. It is common to hear that the charges are exchanging virtual photons. This is not nonsense. In perturbation theory, that language has a clear meaning. But if one takes it too literally, one starts picturing a continuous stream of tiny, unreal photons being hurled between the charges like microscopic snowballs. The field picture becomes replaced by a frantic little traffic system. That is not really a simplification. It is just a change of metaphor, and often a more misleading one. The classical field description already gives a clear account in its own regime. The quantum exchange language refines the formal structure, but it does not require us to believe in a literal swarm of temporary courier particles as the hidden furniture of the force. A similar issue appears with the strong interaction. One hears that gluons mediate the strong force, and this is certainly true in the theory, but the strong interaction is a marvellous example of how quickly simple exchange pictures can run into trouble. Gluons themselves interact with one another. The theory becomes highly non-trivial. Quarks are confined. The naive image of little particles passing tidy messages starts to look less like insight and more like optimism. The formalism remains powerful. The storyline grows less trustworthy as a literal image. Once again, the field language is the more faithful backbone, even if the exchange language remains useful in appropriate settings. The weak interaction offers its own variations with heavy mediator bosons and very short-range behaviour. Here too, one can say the force is mediated by particular bosons, and in the right context that is good physics. But the deeper lesson remains unchanged. The mediators are not tiny explanatory mascots one can deploy in every context without care. Sometimes they appear as real particles under the right experimental conditions. Sometimes they appear virtually in internal lines. Sometimes the exchange story is illuminating. Sometimes it is just the first rung of a ladder one ought not mistake for the roof. There is another subtlety worth noticing. Human beings often think that a better explanation must replace a field with a mechanism made of smaller things. This is partly because our intuitions are reductionist in a very tactile way. If the field sounds vague, surely the truth must be little bits underneath. But quantum field theory does not really reward that instinct. It does not say there is a field because a cloud of tiny hidden particles is passing messages all the time. Rather, it says the particles themselves are excitations of the field, so the urge to demote the field to a secondary convenience and elevate the particle to the true microscopic machinery is, in many ways, backward. The story we tell ourselves often reflects what feels concrete, not what the theory structurally privileges. This is why it is so important to separate levels of description. A field is part of the formal ontology of the theory. A real particle is an observable excitation of that field under appropriate conditions. A virtual particle is an internal element of a perturbative description involving the same field. These are related, but they are not interchangeable. Confusion enters the room the moment one tries to flatten them all into a single kind of little thing. The field becomes a swarm. The virtual particle becomes a temporary bead. The real particle becomes a miniature billiard ball. Everything starts sounding simpler, and everything becomes less accurate. Of course, physics is always balancing truth and usability. No one wants every introductory explanation to begin with a solemn warning that all intuitions are provisional and all pictures only partially faithful. People need somewhere to start. Yet good explanations should also know when to loosen the picture before it hardens into dogma. With virtual particles, that loosening is especially necessary, otherwise the exchange story becomes a trap. One ends up asking whether the hidden messenger is real, whether it exists for a short time, whether it borrows energy, whether it travels faster than light, and one may never notice that the more basic question is what the field theoretic description is doing in the first place. There is something almost literary about this. The story we tell ourselves is not worthless because it is a story. Stories are how human beings think. The problem comes when a story forgets it is one. In physics, some stories are approximations, some are visual aids, some are calculational metaphors, and some are genuinely robust ways of summarizing deep structure. The exchange particle story sits somewhere in the middle. It is useful, formal, suggestive, and easy to overread. It should be treated with appreciation and suspicion in equal measure, and perhaps that is the most honest mood for this topic. Not cynicism, not enchantment, but disciplined appreciation. Yes, it is meaningful to say that interactions are associated with fields, and, in perturbative language, with exchanged quanta. Yes, the particle language captures real aspects of the theory. Yes, the diagrams and mediator talk help us compute and communicate. But no, this does not entitle us to imagine a literal swarm of tiny unreal messengers flitting through space every time one charged object notices another. The theory is subtler than the cartoon, and the cartoon should know its place. Once one accepts that, another famous source of confusion starts to look rather different. There are certain observable phenomena that popular science writing loves to parade as evidence that virtual particles must be real after all. The Casimir effect is perhaps the champion of that parade. It is often introduced as though two metal plates are being pushed together by the pressure of virtual particles in the vacuum, almost as if the universe were sending in tiny stagehands to make a point. But the moment one understands that forces, fields, and mediator language are already layered with storytelling, one becomes much more cautious about turning such phenomena into courtroom exhibits for the literal existence of virtual particles, and that caution is very much needed, because some of the most famous examples in this area do and do not prove what people confidently say they prove. The Casimir effect is one of those topics that arrives with a reputation already fully dressed. By the time most people hear the name, they have usually also heard the punchline. Put two metal plates very close together in a vacuum, and they feel an attractive force. Then comes the part that really sticks. This happens, people are told, because virtual particles in empty space push the plates together. Outside the plates there are more virtual particles, or more allowed modes, or more vacuum activity, and inside there are fewer, so the imbalance creates a pressure that nudges the plates inward. It is a wonderfully neat little story. It has contrast, drama, invisible activity, and the irresistible suggestion that empty space is crowded with hidden things after all. It is also the sort of story that becomes more dangerous the more confidently it is repeated. The awkward truth is not that the Casimir effect is unreal. Far from it. The effect is real. It has been measured. It matters in certain precise contexts. The awkward truth is that the standard popular explanation often slides from useful shorthand into a claim it does not actually justify. The Casimir effect does not straightforwardly prove that virtual particles are little real things popping in and out of empty space in the everyday sense people imagine. It does not hand us a clean photograph of the vacuum swarming with temporary particlets. It does not force the cartoon to be literal. What it proves is subtler and, in some ways, more interesting. It shows that the quantum vacuum is not physically trivial, that boundary conditions can alter the energy associated with field modes, and that those alterations can produce measurable forces, That is already remarkable. It just does not quite fit on a souvenir postcard. Let us start with the basic setup, because part of the confusion comes from how disarmingly simple it looks. Imagine two flat conducting plates placed very close together, with a small gap between them. They sit in what we would ordinarily call empty space. Quantum field theory tells us that the electromagnetic field, even in its vacuum state, has structure. The presence of the plates changes what configurations of the field are allowed in the gap compared with outside the gap. When one calculates the difference carefully, one finds that the energy of the vacuum depends on the plate separation. That dependence gives rise to a force. The plates are drawn together. Already there is plenty to think about, even before anyone starts tossing around virtual particles like confetti. The key ingredients are the quantum field, the vacuum state, the boundary conditions imposed by the conductors, and the fact that the energy changes with geometry. Nothing in that sentence requires little temporary particles slamming into the plates from one side more than the other, at least not as a literal microscopic movie. The effect follows from the structure of the field and the modification of its vacuum state by the plates. That is the careful version. So why does the more dramatic version spread so easily? Because it feels mechanical. It gives the force a visible style of cause, even if the visibility is only in the imagination. The moment someone says the vacuum is full of virtual particles and the plates block some of them in the middle, the mind relaxes. At last, one thinks, there is a hidden crowd doing the work. Empty space has become busy space. The force has become pressure from invisible traffic. A subtle quantum field theoretic calculation has been translated into something like weather, and weather is easier to picture than altered vacuum mode structure. But that translation costs more than it saves if it is treated as the final truth. The first thing to notice is that the Casimir effect can be derived in more than one way. This alone should make us cautious about assigning too much literal status to any single explanatory picture. One can describe the effect in terms of vacuum energy differences associated with allowed field modes between and outside the plates. One can also understand it in other formulations through the interaction of charges and currents in the materials and how the electromagnetic field responds to the boundaries they create. The existence of multiple valid derivations does not mean the effect is vague or subjective. It means the theory allows several routes to the same observable result. That is often a sign that one should not be too eager to reify the intermediate imagery from any one route. If the only correct explanation were that virtual particles are physically crashing into the plates from outside more than from inside, one would expect that picture to have a uniquely privileged standing. It does not. It is a suggestive way of talking, and sometimes a useful one, but it is not the only way to understand what is going on. That matters because popular science often smuggles in an extra step without admitting it. The effect is real. The virtual particle picture is one way to speak about aspects of the calculation. Therefore, people conclude the virtual particles must be literally real little things. But the conclusion does not follow automatically from the premises. A successful representation is not always a literal portrait. A good comparison might be pressure in a gas. If you have a box of gas and the walls feel pressure, you can explain that in terms of molecular impacts. There, the molecules are real observable constituents of the gas. In the Casimir effect, however, using the language of vacuum pressure from virtual particles tempts people into thinking they are dealing with the same kind of ontology. But virtual particles are not molecules of the vacuum. They are not stable ingredients rattling around in a container. They are internal elements of a perturbative description. The comparison to literal particle pressure sounds friendly and intuitive, but it quietly moves the discussion into the wrong conceptual neighbourhood. There is another difficulty. The plates do not merely sit there like passive barriers, holding back a crowd of tiny invisible projectiles. They are conductors, and what matters is the way they constrain the electromagnetic field. Certain modes are allowed, others are modified, and the vacuum energy changes accordingly. This is a field-theoretic statement. It is not, at root, a statement about a hidden rain of independent little objects. One can tell a pressure story if one likes, but the deeper content is about fields and boundary conditions. The force emerges because the allowed structure of the vacuum depends on geometry. That phrase geometry is worth lingering over. The Casimir effect is sensitive to shape and separation, because what counts as an allowed field configuration depends on the physical arrangement. Change the distance between the plates, and the vacuum energy changes. A force follows from that change. This is a very elegant and very physical result. It says that even the vacuum state of a quantum field can be influenced by the presence of boundaries, and that those influences are not merely decorative. They produce measurable consequences. That alone is enough to show that the vacuum is not classically empty in the old crude sense, but it does not compel the stronger claim that the vacuum is literally full of little temporary particles behaving like a ghostly gas. This point becomes clearer when people try to use the Casimir effect as proof that the vacuum contains particles constantly appearing and disappearing in the ordinary sense. The problem is that the vacuum state is not a state with real particles in it, at least not in the straightforward sense relevant to detector clicks. It is the lowest energy state of the field, with non-trivial properties and fluctuations. When one speaks of virtual particles in this context, one is using a certain language for internal contributions or informal picturing. That language may capture some aspects of the formalism, but it is not forced on us as the only faithful ontology. The effect proves the vacuum has physical content. It does not prove that the best literal picture of that content is a tiny crowd of short-lived particles. One way to feel the distinction is to ask what exactly a detector would register if you placed it between the plates in a static Casimir setup. Not a stream of real photons from the vacuum behaving like ordinary radiation. The effect is not a literal bath of outgoing detectable particles trapped by metal walls in the way the popular image encourages one to imagine. The measurable phenomenon is the force between the plates, not a direct census of temporary particles squeezing through the gap. Again, this does not make the effect less real. It simply tells us that the reality of the effect does not automatically validate the strongest literal reading of the virtual particle story. There is also a broader philosophical lesson here about how physicists use explanation. In practice, a phenomenon can often be understood through several complementary pictures, each useful for certain purposes. The danger begins when one of those pictures becomes famous precisely because it is vivid, and then starts claiming exclusive rights to the territory. The virtual particle explanation of the Casimir effect is vivid. It gives empty space a personality. It makes the vacuum sound busy and dramatic. But once that picture becomes too dominant, it starts flattening the richer field, theoretic understanding into a single cartoon. One ends up thinking the Casimir effect is important, mainly because it proves a spooky fairy tale about particles popping into and out of nothing. In reality, the effect is important because it reveals that the vacuum state of quantum fields is physically structured and responsive to boundaries. If anything, the more careful story is more impressive. It tells us that the vacuum is a state with calculable properties, that those properties depend on the constraints imposed by real materials and geometry, and that the resulting differences can show up in experiment. That is not less remarkable than invisible particles pushing plates together. It is simply less easy to draw in a children's book. Of course, once one says all this, another worry often appears. If the virtual particle picture is not the final literal truth, are physicists just playing games with words? Are they saying one thing in public and another in private? Not exactly. What is happening is more ordinary and more human. Physicists often use shorthand. They use metaphors that are efficient inside a community that knows their limits. They speak loosely when the context can bear it. Trouble arises when that looseness is exported without the warning labels. A phrase that is harmless among experts can become a hardened misconception once it leaves the room. Virtual particles in the Casimir effect are a perfect example. The phrase is not completely meaningless. It is just much easier to overread than many people realize. This becomes especially important when the Casimir effect is used as rhetorical ammunition in larger arguments about nothingness, vacuum energy, or the very nature of existence. People love to say that the Casimir effect proves that nothing is actually something, or that particles can emerge from nothing all the time, or that the vacuum is literally a sea of things trying to become real. These are not careful statements. The quantum vacuum is not philosophical nothing. It is a physical state within a theory. The Casimir effect does not show that absolute non-being is unstable. It shows that the vacuum state of a quantum field, under altered boundary conditions, contributes differently to the energy of a system. That is already profound without needing to borrow drama from metaphysics. One should also be careful not to oversimplify the role of the plates themselves. Real materials are not perfect idealized boundaries. They have conductivity properties, response functions, and limitations. In serious treatments of the effect, these material features matter. This too should warn us against imagining the vacuum story as a simple crowd pressure problem. The phenomenon depends on the interaction between the electromagnetic field and the properties of the conducting surfaces. It is not merely a matter of outside particles bullying the plates inward while inside particles go missing. The actual physics is cleaner and more complicated at once. There is a curious pattern in the way this topic is discussed publicly. People often think that if one corrects the virtual particle story, one is somehow draining the mystery out of the effect. But the opposite is true. The mystery was cheap. It came from turning a careful calculation into a supernatural-style vignette. The real wonder lies in the fact that quantum field theory can take the vacuum state seriously enough to assign its structure, modify that structure with geometry and boundary conditions, and predict a measurable force with extraordinary precision. That is not less strange than the cartoon. It is simply strange in a way that respects the theory rather than replacing it with a haunted dollhouse version of itself. It is worth stressing too that none of this means the language of virtual particles must be banned. It means it should be handled honestly. If one says that the Casimir effect can be described in terms of virtual particles in a certain perturbative picture, fine. If one says that this proves the literal existence of a swarm of tiny temporary particles in the vacuum, that is too much. The effect does and does not prove something. It does prove that the quantum vacuum has measurable physical consequences. It does prove that boundaries can alter vacuum structure in ways that matter. It does not prove that the best literal ontology of the vacuum is a gas of popping particles. That extra conclusion is imported by imagination, not forced by experiment. There is a similar issue in other famous examples people like to mention. Vacuum polarization, Lamb shifts, radiative corrections, all sorts of phenomena can be discussed using virtual particle language. And in each case the temptation is the same. The calculations work, the language is vivid, therefore the internal picture must be literally true in the most naive sense. But physics is more disciplined than that. It lets us use calculational tools and flexible language without demanding that every intermediate image be turned into a tiny hidden object. The Casimir effect is simply one of the most famous places where that discipline tends to be forgotten. Perhaps the cleanest summary would be this. The Casimir effect is evidence that quantum fields and their vacuum states are physically real, in the sense that they have measurable consequences. It is evidence that the vacuum is not a featureless blank. It is not decisive evidence that virtual particles are real particles popping in and out of existence in the way popular imagination pictures them. If one insists on using virtual particle language, one should remember that it is a manner of speaking tied to a formalism, not an X-ray of microscopic reality, with little labels attached. There is also something slightly cautionary here about the relationship between explanation and proof. People often ask what a given phenomenon proves, as though the world were in the habit of validating our favourite metaphors one by one. But experiments usually constrain theories and support structures of description. They do not always endorse one vivid picture over every other possible way of speaking. The Casimir effect supports the quantum field theoretic treatment of the vacuum and of electromagnetic boundary conditions. That is substantial. It does not issue a personal certificate of existence to every image that popular science writers have attached to those calculations over the years, and once one sees that, a great many loose statements begin to look less secure than they first sounded. The famous talk of borrowed energy, fleeting violations, particles sneaking briefly into being and then vanishing before the laws can catch them, all of that suddenly looks like exactly what it is. Not deep truth simplified for the masses, but a chain of metaphors that started out as shorthand and gradually escaped supervision. The Casimir effect does not rescue those metaphors. If anything, it gives us a perfect opportunity to examine how they spread and why they are so hard to kill. Because after one has seen how a real quantum vacuum effect can be explained without turning virtual particles into literal ghost objects, the next misconception waiting in line becomes impossible to ignore, namely the very old and very persistent idea that uncertainty somehow gives the universe permission to borrow energy for a moment and pay it back before anyone notices. That idea has enjoyed an unusually long life, perhaps because it sounds like exactly the kind of rebellious secret quantum physics ought to contain. Ordinary rules, we're told, apply most of the time, but down in the microscopic world there is a loophole. Energy can be borrowed for a brief moment, provided it is paid back quickly enough. Virtual particles pop into existence on this temporary credit, do whatever job the universe needs done, and then vanish before the accounting department notices. It is neat, memorable, and just mischievous enough to become irresistible. One can see immediately why it spread. It turns an abstract principle into a story with suspense. It gives the laws of physics a kind of stern but absent-minded personality. It lets the vacuum sound like a place where little crimes happen too fast to prosecute. It is also one of the most successful misunderstandings in modern science. The trouble begins with the phrase uncertainty principle, which has itself suffered many years of being treated like a vague license for anything strange that someone would prefer not to explain properly. In the public imagination, uncertainty often sounds like ignorance, fuzziness, or a convenient lack of discipline. It is as though quantum physics simply shrugs, says things are a bit blurry down there, and allows whatever needs to happen to slip through the cracks. But that is not what the principle means. The uncertainty principle is not a confession of weakness in the laws. It is a structural feature of quantum systems. It tells us that certain pairs of quantities are not simultaneously sharp in the way classical intuition would like. It is about the mathematical and physical structure of states and measurements, not about nature occasionally taking a short holiday from bookkeeping. The borrowed energy story usually enters through the time-energy version of the uncertainty relation, which is one of the most commonly abused ideas in all popular physics. People hear that there is some connection between uncertainty and energy, and uncertainty and time, and they instantly translate that into a narrative about temporary violations of energy conservation. If the time interval is short enough, they imagine, the universe can afford to be a little careless. It can create a particle pair from nothing, let them exist for a blink, and then tidy everything up before the bill comes due. This is a seductive picture because it feels like a clever compromise between strict law and useful chaos. Unfortunately, it takes a subtle statement and turns it into a fairy tale about cosmic overdrafts. Energy conservation in quantum theory is not a rule that flickers on and off depending on how quickly one looks away. In a theory with time translation symmetry, energy conservation is deeply built in. It is not suspended for convenience. It does not tolerate tiny acts of theft in the basement. What changes in quantum theory is not that conservation goes away, but that states, processes, and intermediate descriptions can involve quantities that do not line up with classical expectations in the simple way a beginner might first imagine. The internal lines in perturbative calculations are not real particles carrying exact on-shell energy and momentum as free observable states do. But that does not mean energy conservation has been violated in the actual process. It means the formalism is being used in a way that should not be narrated as a tiny heist. Part of the confusion comes from how the time-energy relation differs from the more familiar position momentum case. Position and momentum are both represented by operators in a straightforward way within the formalism, and the uncertainty relation between them has a clean structural role in the state description. Time, however, is not treated in quite the same way in ordinary quantum mechanics. The relation involving energy and time is therefore subtler. It is often connected to issues such as the duration over which a system changes appreciably, or the spread in energy associated with unstable states, or the limits on how sharply certain time-dependent processes can be characterized. These are real and important matters. None of them requires the universe to permit literal temporary violations of energy conservation. An unstable state is a good place to slow down and think carefully. Suppose a particle has a finite lifetime. Because it is unstable, its energy is not represented by an infinitely sharp single value in the idealized way that a perfectly stable state might be. There is a spread. That spread is related to the lifetime. This is a real physical phenomenon, and the time-energy relation plays a role in understanding it. But notice what has happened. We are speaking about the properties of states and transitions, not about the system breaking the laws and then apologizing later. The particle is not borrowing energy. The theory is telling us something about how finite lifetime and energy spread are related. That is a much quieter statement and a much more correct one. The same goes for intermediate steps in field theory calculations. Internal propagators are sometimes described as though they represent particles existing briefly with the wrong energy. People then leap to the conclusion that the uncertainty principle has granted a special exemption. But the internal line is not a real particle state whose short lifetime excuses bad behavior. It is an internal contribution in the amplitude. The language of temporary borrowing comes from trying to shoehorn a formal device into the familiar story shape of a particle with a biography. Once one lets go of that demand, the need for the borrowed energy myth fades rather quickly. There is an old habit in science communication of taking any difficult statement and searching for a metaphor with enough mischief to make it memorable. This can work beautifully when the metaphor is disciplined. It can also produce monsters when the discipline is missing. Borrowed energy is one of those monsters. It sounds helpful because it gives people an intuitive handle. But the handle is attached to the wrong door. Instead of learning what the uncertainty principle actually says about quantum states, they learn a little fable about the laws of nature occasionally looking the other way. From that point onward, every strange phenomenon gets explained by the same stock phrase: vacuum fluctuations, borrowed energy, tiny particles appearing and disappearing. It becomes a kind of explanatory confetti thrown over any gap in understanding. One way to see how misleading this is would be to ask what it would mean for energy conservation to fail, even briefly, in a literal physical process. Conservation laws are not like social rules that can be broken if no one notices. They are built into the structure of the theory. If a process truly violated energy conservation, that would not merely be a temporary accounting mismatch. It would mean the theory itself was allowing something far more drastic than the popular story suggests. But in actual quantum field theory calculations, what is conserved at the vertices and in the total process is handled rigorously. The internal objects are not excuses for violation. They are parts of the mathematical machinery that do not correspond to free observable particle states in the naive sense. There is also a psychological reason the myth survives. It flatters a certain kind of imagination. It suggests that reality is full of tiny acts of daring. The vacuum becomes a place of flirtation with the forbidden. The laws become negotiable if you are quick enough. There is almost a childish delight in this picture, and perhaps that is why it is so difficult to dislodge. A careful explanation about the spectral width of unstable states, or about the role of off-shell internal propagators, simply does not produce the same dramatic glow. It sounds sober. It sounds technical. It sounds like something one might have to think about twice. And yet, sober is sometimes the correct mood. The phrase off-shell is useful here precisely because it avoids the criminal undertones of borrowed energy. A virtual particle is off-shell in the technical sense that it does not satisfy the same relation between energy and momentum as a real, free particle state. But this is not a report about a particle temporarily existing with stolen resources. It is a statement about the role of the internal line in the formalism. The internal contribution is not constrained to the physical mass shell, because it is not a freely existing external particle. It is part of the integrated internal structure of the amplitude. This may feel less cinematic, but it is much closer to the truth. One might reasonably ask how the borrowed energy myth became so widespread if it is so bad. Part of the answer is historical. In older pedagogical settings, physicists themselves sometimes used loose language to build intuition quickly, especially when speaking to students who are not yet ready for the full formalism. Under those conditions, one might say something like, think of it as a fluctuation allowed for a very short time. Within a room full of people who understood the limits of the remark, that could be harmless enough. But once the phrase escaped into books, documentaries, and second-hand explanations, the warning labels fell off. What remained was a vivid idea detached from the technical discipline that had once kept it in check. Another part of the answer is that uncertainty itself is already a word doing dangerous work. In common speech, uncertainty suggests a defect in knowledge or control. So when people hear that energy and time are uncertain in some relation, they immediately imagine that exact values are simply not being enforced. The theory, however, does not use uncertainty in that loose, everyday way. It is talking about the structure of quantum states, the limits of simultaneous sharpness, and the behavior of observables in a formal setting. The ordinary word uncertainty ends up smuggling in a whole cloud of associations that quantum theory never agreed to host. This is especially obvious when people say things like the particle can exist for a short enough time that you cannot catch the energy mismatch. That sentence is wrong in almost every interesting way. It treats time as though it were a hiding place. It treats the mismatch as a literal violation. It treats detection as though the laws only matter if we happen to notice the offence. And it turns a precise formal relation into a little police procedural. All of that comes from trying to force abstract theory into a vivid but badly behaved image. There is a better way to build intuition, though it requires a little more patience. Instead of saying the vacuum borrows energy to create virtual particles, one can say that quantum field theory describes the vacuum as a non-trivial state of fields, and perturbative calculations of interactions involve internal contributions that are not themselves real particle states. Instead of saying energy conservation is briefly violated, one can say that internal lines are not on shell and should not be mistaken for free observable particles. Instead of saying the uncertainty principle permits temporary law-breaking, one can say that the relation between energy spread and characteristic timescales is about quantum state structure, not about literal theft. None of these sentences will win a prize for mischief. They do, however, have the excellent quality of not teaching nonsense. This matters because the borrowed energy story does not only distort one topic, it spreads confusion into everything nearby. It muddies discussions of the vacuum. It muddies discussions of Hawking radiation. It muddies discussions of force mediation. It muddies discussions of particle lifetimes and resonances. Once someone has learned that the universe is constantly lending itself energy in tiny amounts, and collecting repayment moments later, every quantum phenomenon begins to look like a variation on the same theme. The theory becomes less like a disciplined structure, and more like a casino with very strict closing hours. At that point, one is not learning quantum physics, one is collecting quantum-themed anecdotes. There is also a subtler casualty. The borrowed energy myth makes genuine quantum strangeness hard to appreciate. Real quantum theory is strange enough without these embellishments. States can interfere. Measurement outcomes are probabilistic in a profound way. Fields have vacuum structure. Particle concepts depend on context. Symmetries enforce conservation laws with extraordinary power. These are deep and difficult ideas. But if the beginner is handed a bag full of easy but misleading stories instead, they may never get far enough to notice what the theory actually says. The false strangeness crowds out the real thing. Sometimes people defend the myth by saying that it is not literally correct, but it points in the right direction. I think that is too generous. A good heuristic should become more helpful as one learns more. This one usually becomes a nuisance. The moment a student asks sharper questions, the borrowed energy story starts causing trouble. Why does the particle need to pay the energy back? Who keeps track? How is the time interval determined? Why does the uncertainty principle apply this way here but not elsewhere? Why can these temporary particles not simply be detected before they vanish? Why does the same logic not permit all sorts of absurd processes? The heuristic does not merely leave details out. It actively sets the student up to ask questions framed in the wrong ontology. There is a lesson here about the kind of beauty we should trust. Some misunderstandings are beautiful because they are tidy, vivid, and easy to repeat. They have a polished sort of elegance. Borrowed energy is like that. It feels almost too perfect. A strange world, a temporary exception, a rule bent but not broken. It sounds like excellent storytelling. But in physics, the most beautiful explanations are not always the ones that sparkle first. They are the ones that remain solid when the questions get harder. The borrowed energy story tends to crumble precisely where the real theory becomes interesting. If anything, the truth is more dignified. Energy conservation remains intact. Quantum states can have spreads in energy related to lifetimes and dynamics. Internal elements of perturbative calculations are not real particle states and need not obey the same constraints as external observable ones. The vacuum is structured, but not as a lawless marketplace of stolen quanta. This is less dramatic, perhaps, but far more impressive. It means the theory is not surviving by loophole, it is surviving by coherence. One of the nicest signs that the myth is unnecessary is that physicists doing serious calculations do not need it. They do not derive radiative corrections by imagining a swarm of tiny felons in the vacuum. They do not compute scattering amplitudes by appealing to momentary legal exceptions. They use the formalism. They calculate propagators, amplitudes, loop contributions, renormalize quantities, state widths, correlation functions. The borrowed energy story does not do the real work. At best, it is a rough public gloss. At worst, it is a persistent distraction dressed up as insight. And perhaps that is why it is worth being a little stern with it. Some misunderstandings are harmless. This one is unusually sticky because it plugs into so many neighbouring topics. It turns the uncertainty principle into a vague permission slip. It turns virtual particles into tiny counterfeiters. It turns the vacuum into a stage magician. All of this makes quantum field theory sound wonderfully naughty and much less disciplined than it really is. The truth is not that the universe is cheating. The truth is that our language has been cheating us by pretending a metaphor was a mechanism. Once you see that, virtual particles begin to lose the last of their ghostly glamour. They are not little temporary beings financed by quantum debt. They are internal components of a calculational framework. Their off-shell nature is a formal feature, not evidence of secret law-breaking. The uncertainty principle is not their sponsor. It is a deep statement about quantum states that has been repeatedly forced to wear costumes it never asked for. And with that costume finally coming off, the whole subject starts to look less like a haunted subatomic theatre, and more like what it really is, which is a very powerful formalism surrounded by a surprising number of human attempts to make it sound like folklore. That is the point at which another image begins to seem much more appropriate. If virtual particles are not ghost objects, and not temporary violations made respectable by haste, then perhaps the best way to think of them is not as hidden residents of reality at all, but as something closer to bookkeeping devices that have acquired a mythology by being too visually charming and too verbally convenient for their own good. That word bookkeeping can sound a little deflating at first, almost rude, as though we'd taken one of the most famous ideas in modern physics and quietly moved it into a drawer labelled office supplies. People hear that virtual particles are bookkeeping devices or accounting tools and sometimes react as though something valuable has been stolen from them. They were promised strange hidden activity in the vacuum, tiny messengers darting between particles, brief flashes of existence. And now the story has been replaced by ledgers, organisation, and internal consistency. It can feel like being told that the monster in the attic was only the plumbing. Useful, perhaps, but not nearly as satisfying over tea, and yet bookkeeping is not a bad word here. In fact, it gets us much closer to the truth than most of the dramatic alternatives. The trick is to understand what sort of bookkeeping physics is doing, and why an accounting tool in a theory can still be deeply meaningful without being a little object hiding in the world. When physicists say that something is a calculational device, they do not mean it is nonsense. They do not mean it is arbitrary, decorative, or made up in the careless sense. They mean that it belongs to the internal machinery by which the theory organises and produces correct predictions. That may sound less romantic than the picture of tiny temporary particles, but is actually a more impressive role. A good accounting tool in physics is not like a doodle in the margin. It is more like a carefully designed system for keeping track of contributions that would otherwise overwhelm the calculation. It is part of the discipline that lets the theory speak clearly. This is worth emphasising because people often slide from not directly observable to unreal, and from unreal to unimportant. That is too quick. Science uses many things that are not directly observable in the simple everyday sense. Fields are not seen the way chairs are seen. Wave functions are not pebbles one can put in a jar. Centres of mass, normal modes, effective potentials, even coordinate systems themselves are all ways of organising physical description. Some of them correspond more directly to what the world contains, some less so, but all can be indispensable in the right framework. Their value lies in what they let us state, predict, and connect. Virtual particles belong in that kind of company. The mistake is not in saying they are tools. The mistake is in hearing tool and assuming toy. A financial ledger is not money. That much is obvious. Still, without the ledger, a complicated enterprise may become unreadable. The transactions are real, the balances matter. The profit or loss is not imaginary. But the entries in the ledger are part of the representation of that activity, not little coins stored between the pages. Something similar is going on in perturbative quantum field theory. The interactions are real. The measured outcomes are real. The corrections to masses, charges, and scattering probabilities are real in the sense that they show up in experiment. But the internal virtual particles that appear in the diagrams and intermediate expressions are part of the theory's ledger. They help organise the contributions. They are not tiny bits of reality tucked inside the event, like receipts stapled to the underside of the universe. This is especially important because the ledger in question is not merely practical. It is highly structured. Every internal line, every vertex, every loop, every combinatorial factor is constrained by the form of the theory. The bookkeeping is not loose. It reflects symmetries, conservation rules, interaction strengths, and the entire architecture of the field theory. In that sense, calling virtual particles accounting tools is not meant to trivialize them. It is meant to place them where they belong. They live in the internal accounting system of the perturbative expansion. They are not the final public statement of what the experiment contains. They are part of how the theory keeps itself honest while getting there. There is also a useful distinction between hidden and internal. A hidden object is the sort of thing one might imagine existing out in the world, whether or not we currently detect it. An internal element of a formalism is not hidden in that same sense. It is not waiting patiently behind the curtain for better instruments. It is part of the specific way the theory has been arranged for calculation. This is why virtual particles are not merely undetected particles. They are not particles we have not yet caught. They are not shy members of the same category as ordinary detected particles. They are internal components of the mathematical description. To think of them as hidden residents of nature is already to have crossed into the wrong picture. The word ghost can be useful here, provided we keep it on a short leash. A ghost in ordinary language is something that seems present without being fully there. something that influences the story without belonging to the furniture of the everyday world. That is not a terrible first metaphor for virtual particles, as long as one resists the temptation to make them supernatural inhabitants of the vacuum. Physics is not filling space with spectres. It is using particle-flavoured language for internal contributions that never become directly observable particle states. They haunt the calculation, not the laboratory in the simple sense. The detector does not find a little graveyard of unreal particles after the experiment. It finds the actual measurable outcomes. The ghosts did their work in the arithmetic. Part of the reason this matters is that physics often permits different internal accounts of the same observable reality. This is a devastating clue against taking every intermediate object too literally. If one can change the formal arrangement, the gauge, the perturbative organization, or the representation while keeping the final observables fixed, then one should be very careful about promoting one particular set of internal entities into permanent furniture of the world. The final measurable quantities are robust. The internal root can vary. That does not make the internal root meaningless. It means its meaning is tied to the role it plays in the formalism, not to a simple one, to one claim that each internal line corresponds to a tiny object, really buzzing about in empty space. Think about directions on a map. There may be several ways to get from one city to another. One route uses highways, another uses smaller roads. A rail map gives a different picture from a driving map, yet both may guide real travel. The fact that multiple representations can guide you toward the same destination should make you cautious about declaring every mark in one map to be literally painted on the landscape. The marks are not fake. They're useful because of the real structure of the territory, but their status belongs to representation. Virtual particles are like that. They arise because the theory has real structure. Their usefulness is not arbitrary, yet they do not owe us literal objecthood simply because they appear in one particularly elegant map of the calculation. This becomes even clearer when one looks at higher order corrections. At the simplest level, people are already tempted to misread a single exchange diagram as a miniature event. But the real predictive power of quantum field theory often depends on adding loops and other more complicated contributions. These internal structures affect measurable quantities in subtle and important ways. They help account for the way observed values differ from the simplest naive expectations. A particle's effective mass, the strength of an interaction, the precise probability of a scattering outcome, all of these can depend on such corrections. If one insists that every loop is a literal swirl of temporary particles performing a tiny dance in the vacuum, one quickly finds oneself telling stories that are harder and harder to defend. The better interpretation is the quieter one. The loop is part of the accounting. It records how the theory corrects itself when the interaction is treated more carefully. There is something mature about this sort of quietness. The beginner often wants each successful prediction to come with a vivid little film, but science does not always pay in films. Sometimes it pays in reliable structure. We compute a quantity, compare it with experiment, and find astonishing agreement. That agreement is the achievement. The internal narrative one attaches to each mathematical piece may be more or less helpful, more or less faithful, but it is not the main prize. In virtual particles, the prize is not that we have discovered microscopic sprites ferrying forces around. The prize is that perturbative quantum field theory has a disciplined way of organizing interaction contributions so well that the resulting predictions match nature with extraordinary accuracy. Bookkeeping is also a better word than mechanism in this context, because it avoids a common trap. A mechanism, in ordinary thought, is usually something like gears, levers, or identifiable components acting in a sequence. It invites one to imagine the real process as a chain of tiny operations. But much of modern field theory does not reward that style of imagination. The mechanism, if one insists on the term, is not a clockwork hidden beneath appearances. It is the structure of the theory itself, the way fields interact, the way amplitudes are assembled, the way symmetries constrain what may happen. Virtual particles are then part of the accounting of that structure, not the gears one would find if only one could shrink enough to crawl inside the event. That last fantasy is especially persistent. There is an almost cinematic desire to become very small, slip into the gap between two interacting particles, and watch the hidden exchange happen. One imagines seeing the virtual photon zip by, or the loop briefly whirl into being, or the vacuum flicker with tiny traffic. But if one could somehow enter the world at that scale, the theory does not promise a classical spectator's view of such little events. The urge to watch is itself part of the problem. It assumes the world is arranged as a miniature theatre whose props are exactly the same props that appear in our chosen diagrams. That is a flattering assumption for the human imagination. It is not one physics is required to satisfy. The accounting metaphor helps because it reminds us that internal consistency can be real without being visible in the same way as the final outcome. If a bridge stands, the calculations that ensured its stability were not imaginary just because they were never poured into concrete. If a vaccine works, the molecular modelling that guided its design was not unreal just because the models were not tiny copies of the finished medicine. Likewise, if a particle physics prediction lands on the right number to many decimal places, the internal structures used in the theory were doing real conceptual work, even if not every one of them corresponds to an independently existing object one could detect with its own little name tag. There is a further point that often gets missed. Calling virtual particles accounting tools does not mean they could be replaced by any random set of invented helpers. The formalism is constrained. Not every story will do. Not every notation will preserve the structure of the theory. Virtual particles arise in a specific mathematical context. They are not made up in the sense that dragons or elves are made up. They are closer to the way a contour line on a topographic map is made up. The line itself is part of the representation, yes, but it faithfully encodes something about the shape of the terrain. You should not go looking for the contour line painted on the hillside. You should also not call it meaningless because it is not painted there. Its value lies in how well it tracks the real structure. Virtual particles function in much the same spirit. This is why the phrase mere bookkeeping is unfortunate, even when people use it to correct misconceptions. The word mere suggests dispensability. In physics, a bookkeeping device can be the difference between a theory that is usable and one that is hopelessly unwieldy. It can preserve the logic of the calculation in a way the unaided human mind could not. It can reveal which contributions matter and which can be neglected. It can expose symmetries and cancellations that would otherwise remain buried. There is nothing slight about that. The fact that a thing belongs to our formal accounting does not demote it to a joke. It simply places it where honesty requires it to be placed. The same honesty also helps with a frequent emotional reaction people have when this topic becomes clear. They sometimes feel that the universe has become less vivid, as though the correction from tiny hidden particles to internal accounting has drained some of the strangeness away. I think the opposite is true. The old picture was strange in a rather cheap theatrical way. It gave you a ghost story. The better picture gives you something more durable. It shows that nature can be successfully described by a formal system whose internal architecture does not line up neatly with the object-centered imagination we evolved for everyday life. That is a deeper strangeness. It says the world is not merely crowded with weird little things. It says the very way a theory organizes reality may refuse to collapse into the sort of tiny narratives our intuition prefers. In a sense, this is more adult wonder. The child wants monsters in the walls. The adult starts to appreciate the blueprints. There is another subtle advantage to the accounting view. It helps explain why arguments over whether virtual particles are real often become sterile. Usually the two sides are quietly using different standards of reality. One side means real, as in directly observable particle state. Under that standard, virtual particles are not real. The other side means real as in mathematically indispensable to a successful physical description. Under that standard, dismissing them entirely seems too harsh. The argument then spins in place because the word real is doing too much work. Once you say that virtual particles are internal formal entities with genuine calculational significance, but not the status of observable particles, most of the heat drains from the debate. The ghosts return to the ledgers, and everyone is a little calmer. This also helps us avoid a common rhetorical trap. Sometimes one hears that because virtual particles are not real particles, they therefore cannot explain anything. That is not right either. Internal entities in a theory can still participate in explanation, provided one is clear about the level of description. A free body diagram explains the balance of forces on a ladder without being a little ladder hidden behind the ladder. A line of latitude helps explain navigation without floating in the ocean. Likewise, virtual particles can help explain how perturbative field theory organizes interactions without being literal hidden objects. Explanation is not always a census of tiny furniture. Sometimes it is an account of structure. Of course, the structure matters most where the theory is actually used. When physicists calculate scattering amplitudes, radiative corrections, or transition rates, they are not asking whether a virtual particle really had a short but meaningful life somewhere behind the data. They're asking how the formal contributions combine to yield the observed result. The internal lines, the loop terms, the propagators, the renormalized parameters, all of these belong to that task. The language becomes almost businesslike. The calculations do not need mythology. The mythology was added later for the comfort of those watching from outside. That is why ghosts as accounting tools is not a dismissal but a correction of perspective. It says that the mystery, where it exists, belongs to the formal relationship between theory and observation, not to a hidden menagerie of almost real particles sneaking through the vacuum. The ghosts are not household residents of the cosmos. They are the shorthand marks by which the theory keeps track of itself. They have no detector address. They do not line up for inspection. They are useful because the mathematics has found a way to speak economically about interactions that would otherwise be painfully difficult to describe, and perhaps that economy is part of the beauty. Human beings built theories with such precision that even their internal accounting acquired evocative names and visual forms. Those names then escaped into public life and turned into legends. That is a very human thing to happen. We invented a ledger and then wrote folk tales about the columns. The sensible response is not embarrassment, only clearer speech. We can keep the elegance without mistaking it for a hidden zoo. By now then, a more stable picture has started to form. Virtual particles are not tiny temporary residents of empty space. They are not bits of illicit energy with excellent timing. They are not the final microscopic mechanism of force in the way old mechanical intuition would like. They are internal, formal, particle-flavoured elements of a perturbative bookkeeping scheme that helps quantum field theory produce accurate predictions. That's already a lot to say, and it is far more precise than the folklore version. Still, one last task remains, and it is the most direct one of all. After all the clearing away of myths, after the diagrams, the vacuum, the Casimir effect, the borrowed energy story, and the accounting ledgers, we still need to say as plainly as possible what a virtual particle really is, and why, in the sense that matters here, it is not real. By this point, the phrase virtual particle has probably lost some of its old glamour, which is not necessarily a bad thing. A good many ideas in physics become clearer the moment they stop sounding like props from a magic show. And that really is what has been happening all along. We began with a phrase that seemed to promise tiny hidden beings flickering in and out of existence, doing useful work in the dark and slipping away before anyone could get a proper look at them. It sounded vivid. It sounded dramatic. It sounded as though the universe had a backstage full of impatient little understudies waiting to run on, deliver a line, and vanish into the wings. But the more carefully we looked, the less that picture held together. So now we can finally say it plainly. A virtual particle is not a small object secretly flying around inside nature in the same way a real detected particle can. It is not a temporary version of an ordinary particle. It is not a particle with a shortened life and flexible morals. It is not a tiny measurable thing that almost exists but does not quite commit. In the sense that matters in quantum field theory, a virtual particle is an internal feature of a perturbative calculation. It is the name we give to an internal line in a Feynman diagram and to the corresponding contribution in the mathematical expression for an interaction amplitude. That is what it really is. That answer can sound a little austere at first, so it is worth taking slowly. When physicists calculate the probability that one set of particles will scatter into another, or that a process will occur in one way rather than another, they often use perturbation theory. That means they build the answer as a series of contributions. The contributions can be organised with diagrams. In those diagrams, the incoming and outgoing lines correspond to the particle states that can actually be prepared and detected. The internal lines represent intermediate contributions to the amplitude. Those internal lines are what we call virtual particles. Already, if one is listening carefully, the difference is sharp. The real particles are the ones that can begin or end the process as actual observable states. The virtual particles are the internal pieces of the calculation that help determine the probability for the process as a whole. They are not separately prepared. They are not separately detected. They do not emerge from the experiment as proper standalone objects. They belong to the inside of the formalism. This is why the word real becomes so important and so slippery. In everyday speech, real often just means genuine, not imagined. But in this context, a real particle means something more precise. It means a particle state that satisfies the physical conditions required of an actual observable excitation of the field. It can exist as an incoming or outgoing state. It can, in principle, travel to a detector and leave a signal. A virtual particle does not have that status. It is associated with the same field, yes, and it inherits particle language because of that association, but it is not a real particle state in that technical sense. You can think of it like this. Suppose you are describing a journey. The real particles are the people who actually depart from one station and arrive at another. The virtual particles are more like the internal route segments on the planning map that help you calculate all the possible ways the trip can unfold. Those route segments matter. Change them and your answer changes. But they are not themselves travellers standing on the platform waiting to be counted. They are part of the structure of the description. This is also why virtual particles are often said to be off-shell, which is just the technical way of saying they are not constrained like real free particle states. A real particle has to satisfy the relation appropriate to its mass, energy and momentum as an actual observable excitation. A virtual particle does not. Its associated quantities are internal to the calculation and are integrated over in a way that reflects its role in the amplitude, not its status as a thing out in the world. That is not defect. It is the whole point. The virtual particle is not failing to be real. It was never applying for the job in the first place. Once that sinks in, a great many common phrases start to look less trustworthy. The idea that virtual particles pop in and out of existence begins to sound like what it is, a vivid but misleading way of talking about internal features of a formal expansion. The idea that they borrow energy for a short time begins to collapse even faster. Energy is not being secretly stolen and repaid before the laws can notice. What is happening is that the internal lines are not real observable particles, and forcing them into the story shape of tiny temporary beings produces exactly the sort of misunderstanding that has haunted this subject for years. There is a useful honesty in admitting that physics sometimes uses names which are better than silence and worse than precision. Virtual particle is one of those names. It is better than silence because it points to a real and important part of the formalism. It tells trained physicists something useful about the structure of a calculation. But it is worse than precision because it invites the imagination to picture a little particle where there is really an internal propagator contribution in an amplitude. The name survived because it is convenient. Convenience, as we've seen, is not always a reliable guide to ontology, and yet one should be careful not to swing too far in the other direction. Saying that virtual particles are not real particles does not mean they are meaningless. It does not mean the effects associated with the calculations are unreal. It does not mean physics has been playing a trick. The formalism works astonishingly well. The internal contributions matter enormously. They are part of how the theory delivers predictions of extraordinary accuracy. If you remove them, the calculations fail. So the right attitude is not dismissal, but discipline. Virtual particles are not little hidden objects. They are real features of a successful mathematical framework. That is a subtler kind of reality than popular explanations often promise, but it is still a serious one. This is where the field concept becomes the steady anchor. In quantum field theory, the fundamental entities are fields. Particles are excitations of those fields. Real particles are observable excitations that can show up as incoming or outgoing states. Virtual particles are internal features of perturbative descriptions involving those same fields. In other words, if you try to imagine the world as a box full of tiny objects and then treat virtual particles as the ghostlier members of the box, you are already beginning from the wrong end. The theory is field-based from the start. The particle picture is useful, but it is not the whole foundation, and the virtual particle picture is even further from being basic furniture. The clearest sign of this is that the same physical effect can often be understood without leaning on virtual particle talk at all. The Casimir effect is a perfect example. Popular accounts love to describe it as pressure from virtual particles, but the effect can also be understood through the way boundary conditions alter the vacuum structure of the electromagnetic field and change the energy of the system. Likewise, many radiative corrections and interaction effects can be formulated in ways that do not require a cartoon of tiny temporary beings doing errands in the vacuum. The formal language of virtual particles is useful in certain calculational contexts, but the physical content does not stand or fall with the literal reality of the cartoon. That is often the best test in science. If a picture is truly the final literal mechanism, then it should be hard to do without it. If the same theory can express the same measurable reality through multiple equivalent routes, then one should be cautious about elevating one especially vivid picture into a compulsory hidden movie of what nature is really doing. Virtual particles fail that test of compulsory literalness. They are helpful. They are not mandatory as tiny ontology. There is also a deeper reason why the misunderstanding is so hard to give up. Human beings love little moving things. We trust them. We understand a world of pebbles, droplets, billiard balls, letters passed from hand to hand. Fields are harder to picture. Amplitudes are harder still. So when a theory offers us a line in a diagram and lets us call it a particle, our minds leap gratefully back toward old mechanical comfort. At last, we think, here is something small and busy and object-like. Here is a way to turn the abstract back into a tiny story. It is a perfectly human impulse. It is just not always a reliable guide to what the theory means, and perhaps that is why this topic matters beyond its own small corner of physics. It teaches a more general lesson about how science works. Not every successful part of a theory is best imagined as a little thing hiding in the world. Sometimes the theory succeeds because its internal language is richer, more flexible, and less pictorially literal than our common sense prefers. Sometimes a line in a diagram is exactly that. A line in a diagram, even though it carries serious physical meaning in the calculation. Sometimes understanding means learning not to overdraw the picture. There is a kind of maturity in that. Early on, one wants science to provide tiny hidden mechanisms for everything. Later, one begins to appreciate that the deepest theories often give us something different. They give us structures, relationships, symmetries, and formalisms that predict the world with remarkable precision, while refusing to collapse neatly into the miniature stories our ancestors might have preferred. That is not a weakness of science. It is one of the strongest signs that the world is not obliged to resemble the inside of our heads. Still, one can ask a fair question. If virtual particles are not real in the relevant particle sense, why not drop the term altogether and replace it with something more careful? There is a practical answer and a human one. The practical answer is that the term is deeply entrenched and technically useful inside a certain style of calculation. Physicists know what it means in context. The human answer is that once a phrase becomes vivid enough, it is almost impossible to evict. Language settles in. It brings its habits with it. And then every new generation has to learn both the term and the caution that should always have accompanied it. There is something almost endearing about that. Physics, for all its rigour, is still done by people. People coin names, teach with shortcuts, draw diagrams and tell stories. Some of those stories are excellent stepping stones. Some become weeds. Virtual particle managed to be both. It helped generations of physicists talk efficiently within perturbative quantum field theory. It also gave popular science one of its most persistent little myths. The same phrase that is technically serviceable in one room becomes badly misleading in another. That is not a cosmic mystery. It is simply what happens when elegant shorthand escapes supervision. So what a virtual particle really is, in one careful sentence, is this. It is an internal off-shell contribution associated with a field in a perturbative calculation of a quantum process, often represented by an internal line in a Feynman diagram, and useful for organizing the amplitude that determines observable outcomes. And why is it not real? Because it is not an independently existing, on-shell, observable particle state that can appear as a genuine incoming or outgoing excitation and be directly detected in that role. It belongs to the inside of the calculation, not to the detector readout as a particle in its own right. That answer may not have the flash of the old stories, but it has the considerable advantage of being true. And maybe truth, once it has settled in properly, is more satisfying anyway. The vacuum does not need to be crowded with tiny ghost particles to be interesting. Quantum fields do not need to break the rules for brief dramatic moments in order to be strange. Feynman diagrams do not need to be microscopic photographs in order to be brilliant. The universe is under no pressure to entertain us with little hidden cartoons. It is already offering something rarer and more demanding, a structure that can be understood, but only if we are willing to loosen our grip on the kinds of pictures that feel easiest at first. That is, in its own calm way, rather beautiful. We began with a phrase that sounded like science fiction, and arrived at a lesson in theoretical discipline. We started with little imagined beings flickering in and out of existence, and ended with the more careful insight that physics often works through formal structures whose internal elements are meaningful without being tiny things in the world. We discovered that a name can mislead while still pointing to something important. We discovered that the vacuum can have structure without becoming a haunted house. We discovered that uncertainty is not a permission slip, and that bookkeeping can be one of the most powerful forms of understanding there is. And perhaps most usefully of all, we discovered that the right response to a vivid scientific phrase is not always awe at the picture it suggests, but curiosity about whether the picture was ever meant to be taken literally. That little habit of mind is worth carrying into many other corners of physics. Theories are full of handholds, shortcuts, inherited names, and metaphors that work beautifully until they begin to pretend they are the whole truth. When that happens, it helps to slow down and ask what the mathematics is actually doing, what the experiment actually measures, and what sort of thing the theory is really asking us to believe in. If you do that here, the answer becomes surprisingly clear. A virtual particle is not a tiny hidden resident of reality. It is part of the way a successful theory keeps track of interactions. It matters, it contributes, it helps produce the numbers that match the world. But it is not real as a particle in the sense that a detected particle is real. It never truly arrives in that form. It never stands on its own as the kind of observable object the name encourages us to imagine. So the next time you hear someone say that empty space is full of particles constantly popping in and out of existence, or that the vacuum is borrowing energy by the handful, or that forces work because tiny unreal messengers are forever zipping between particles like overworked postmen, it may be worth pausing for a moment. Not to spoil the fun entirely, but to replace one kind of wonder with a better one. The better wonder is that we have a theory capable of describing interactions with extraordinary precision, and that the path to that success runs through concepts that are useful without always being literal, powerful without always being picturable, and real in the formal sense without being real in the simple object sense. And now, after all that talk of fields, forces, diagrams, and the stubbornly misleading career of the virtual particle, there is something rather pleasant about returning to the quiet simplicity of the room around you. A chair is still a chair. A cup is still a cup. The air is not full of tiny ghostly beads waiting for their chance at existence. It is just late, perhaps, or nearly late, and the world has hopefully become a little clearer than it was when we began, which is not a bad outcome at all for an evening spent asking what a virtual particle really is, and why, in the most important sense, it is not real.